closed forms. Negate P, the proposition to be proved by resolution, that is my P proposition, we negate that and convert the result to the closed form. We convert the proposition that is to be proved by resolution, we negate it, and negated expression, we convert that into the closed form and add it to the set of clauses obtained in step number 1. So available set of axioms converted into the closed form. We start with the goal, negate the goal, and that negated goal we convert into the closed form. So that is my set of clauses available after step number 2. Add it to the set of clauses obtained in step 1. Repeat until either a contradiction is found or no progress can be made. Repeat until either a contradiction is found or no progress can be made. And here are the steps to be repeated till a contradiction is found or no progress can be made. And step number 1. These are the 3 steps to be followed. Steps A, B, C. So let us look into step number A. Select 2 clauses. We have a set of clauses ready using steps number 1 and 2. Select 2 clauses and call these parent clauses. Select 2 clauses, call these parent clauses. Resolve them together. What is meaning of resolving them together? The resulting clause, we will select 2 clauses, will resolve them, and the meaning of resolving them is the resulting clause called the resolvent will be the disjunction of all of the literals of all of the parent clauses with the following exception. If there are any pairs of literals L and not L, such that one of the parent clauses contains L and other contains not L, then select one such pair and eliminate both L and not L from the resolvent. Let's repeat that. Resolve them together. So we have to select 2 clauses, and these are called parent clauses as per the terminology of algorithm propositional resolution. And which 2 clauses to select? So select clauses in such a way that one of the parent clauses contains a literal in the positive form and the other contains a literal in the negated form. Other contains the literal in the negated form. So if there is a literal which is in the positive form, for example literal L, then the other clause must contain this particular literal in the negated form. So we must have not L. So resolve them together. The resulting clause called the resolvent will be the disjunction of all of the literals of all of the parent clauses with the following exception. If there are any pairs of literal L and not L, there must be pairs of literal L and not L. There should be our selection. If there are any pairs of literals L and not L, such that one of the parent clauses contains L and other contains not L, then select one such pair and eliminate both L and not L from the resolvent. So select 2 clauses such that one contains L and other contains not L, and the resolvent will be total, everything of the 2 parent clauses except L and not L. So basically we eliminate L and not L, except these 2 literals we write everything, and that is my resolvent. That is meaning of A. That is meaning of B. Let us go to meaning of C. Step C. If the resolvent is the empty clause, then a contradiction has been found. If it is not, then add it to the set of clauses available to the procedure. The resolvent is the empty clause, then a contradiction has been found. That is our ultimate objective, to find a contradiction. If it is not, then add it to the set of clauses available to the procedure. It means the negated clause is consistent with the database, not the original clause. Original clause is not true. That is not provable. The negated clause is consistent with the database, and we can add that negated clause to the set of the clauses available to the procedure. Here is the example, very simple. Let us not worry much about those steps. Not difficult to understand these steps. Steps 1, 2, 3. Substeps A, B, C, will apply all of them, whichever are applicable. So let's take example. A set of axioms given to us, basically first order expressions, they are 1, 2, 3. P over Q, P implies Q, Q implies R. So when we convert this into the closed form, basically we are removing all operators except the OR operator. We are writing these expressions in terms of OR operator. So my clause number 1, it is anyway in terms of OR operator, that is P over Q, no change. My clause number 2 becomes P implies R, that is not P or R. We are writing expression in terms of the logical operator or. That is my closed form. By default, all these clauses are related by the AND operator. It is C1 is true, and C2 is true, and C3 is true. Similarly, C3 is not Q or R. These are C1, C2, C3 clauses. My goal is to prove R. The goal to prove R. Proof by contradiction. That's the principle of resolution. And my step number one always is negate the goal. We have converted, go back to the algorithm. We have converted the axioms or the first order predicate logic expression into the closed form. Convert all the propositions of F, a set of axioms, to the closed form. It means we are writing expression in terms of OR operator that we have done. Step number two, negate P, the proposition that is to be proved by resolution, and convert the result to the closed form and add it to the set of clauses obtained in step number one. So, my step number two, I want to prove R. My goal is to prove R. I negate the clause. There is no operator available. This itself is a literal. The smallest formula, the smallest atomic formula, single literal. I negate that. That is not R, and that I have added to the set of clauses available to the procedure. Already C1, C2, C3 are available. Now to the procedure, the resolution procedure, C4 is also available. That is not R. You have to forget R. The available clause is not R. So C1, C2, C3, C4 are available to the procedure. And as per the algorithm, we have completed two steps. We have completed two steps. Added to the set of clauses obtained in step number one. So those three clauses plus one more clause, the negated proposition, that becomes my clause fourth. Repeat until either a contradiction is found, and number A, select two clauses, call them parent clauses. So I'll select two clauses. I'm selecting C1 and C2 as per my choice. I can select any clause. Normally we start with the clause that is to be proved, but we can also start with a clause which is not to be proved. In this particular example, we are starting with the clauses and it does not contain a clause to be proved. Usually we start with not R. In this example, we can also start with other clauses to illustrate that we are starting with different clauses. So we are starting with C1 and C2, but the requirement is one of the parent clauses must contain a literal in the positive form and other should contain a literal in the negative form. If that is the requirement, then only we can cancel it out. Otherwise, it will become a lengthier procedure. We can select other thing, but then we cannot eliminate anything. So we have selected C1 and C2 because there is a literal P which is in the positive form and literal not P in C2. It is P present in the negated form. And when we resolve them, my parent clauses, as per the terminology of algorithm, they are C1 and C2. That is my step number 2A, my 3A. Select two clauses, call these parent clauses. My parent clauses are C1 and C2. I have carefully selected them. I may select in any order, but then it will take a longer path. The ultimate goal is to get a contradiction. And by contradiction, we are proving that the negated goal is the cause of the contradiction. Therefore, the original clause is true. So we are selecting two clauses. We can randomly select that clause. That may make our procedure of getting contradiction a lengthier one. So we are taking some care in selecting that, and in fact, we are taking care of step number two. Resolve them together. PB. Resolve them together. The resulting clause will be, or the resolvent will be, disjunction of all of the literals of all of the parent clauses with the following exceptions. If there are any pairs of literals L and not L, such that one of the parent clauses contains L, other contains not L, select one such pair and eliminate both L and not L from the resolvent. We have selected such pair only. We have selected C1 and C2 because P is present in the negated and in the positive form. And my resolvent will be everything except the literal which is there in the positive and the negative form. It means my resolvent will be Q or R. That is my resolvent. C1 and C2, they are parent clauses as per the terminology of the algorithm. Resolvent will be everything from C1 and C2 except the literals which are there, except the literal which is there in the positive and the negative form. Here it is P, so my resolvent is Q or R. We have to discard P, we have to discard not P. Everything else Incidentally, these are smaller expressions. Otherwise, whatever we have written in C1 and C2, we have to write here. So remaining literals in any form, so it is Q or R, that is my resolvent. And this is step number 3, repeat until. It is repeat until. Repeat until the terminating condition for the algorithm is either a contradiction is found or no progress can be made. So there is no contradiction yet. Let us check if we can make progress in the algorithm. Continue. Now Q or R. This is a very simple example. Now in C4, close number C4, we have not R. I can select C3 because there also, sorry, I cannot select, I don't want to select C3 because we don't have, sorry, ignore that. C3 I can select because we have not Q. Currently I have Q, I can select C3. I have a literal in the positive in the negative form. So selecting C3, I will be able to make progress in a systematic way. I can arbitrarily select any clauses, but then there won't be much progress and my path will be lengthier. So I can, at this juncture, I can select C3 because there is not Q. Currently I have Q. I can also select C4 because we have R and in C4 not R is present. So I am selecting C4. And my resolvent is very simple, that is Q. Resolving Q or R with C4, C4 is not R, so R and not R get eliminated, remains Q, and that is my new parent clause. That is my resolvent. That is my resolvent. Q or R, clause number C4, C4 is not R, so R and not R get cancelled out, remains Q, that is the resolvent. And now I am selecting C3 because there is not Q. At the previous point also I could have selected C3, ultimately same answer we would have got in same number of steps. So Q and C3, C3 contains not Q, currently I have Q, Q and not Q cancelled out, remains R. And once again for R, I select C4 because that is not R, and R and C4, I get the required contradiction. So the thing that is not visible is R, C4, C4 is not R, so R and not R, I have nothing remaining, so that is my null set. I get a contradiction, and this is a contradiction because my resolvent means R and C4 has to be true. R and not R has to be true, and R and not R, we know itself is a contradiction, is always false, can never be true. So using R, C4, my current clause is R, I have selected C4, all the clauses are related by the AND operator, so not R and R can never be true, therefore that is a contradiction. Therefore the clause which I have added, that was negated clause not R, that cannot be true. Therefore R is consistent with the database, R is true, not R is false, therefore R. So that is my proof by contradiction technique, example of applying algorithm propositional resolution to our set of axioms given to us. Any doubt? Any question to anyone? Example of propositional resolution. Algorithm we discussed. Algorithm propositional resolution. These steps. We have discussed all the steps. And we know the terminating condition, it is repeat until either a contradiction is found. We found the contradiction, we stopped the algorithm. Therefore, the negated clause, that is false. Therefore, the original clause, that is our conclusion. That is the principle behind resolution, we know. By refutation, and a clause may be proven to be true in the context of a set of clauses known to be true by adding the logical knot of this clause to the set and seeking a contradiction. Anyone has any kind of doubt? Any doubt to anyone? Is that clear to all? So in the next lecture, we'll start applying resolution to first order predicate logic. The previous example, this example, it was applying resolution to propositional logic. From next lecture, we'll start the next topic, that is applying resolution to predicate logic. Okay, fine. Thank you.
Hello everyone, good morning to all of you. I hope I'm audible to all of you and were able to see the presentation on your screen. So let us begin our lecture with where we left in the last lecture, that is last week. So I'm going to revise one slide, okay, so that you have an idea of what we are discussing. We have started with a new topic, that is semantic analysis, okay, and all of you by now are very clear that where is the semantic analysis phase in the sequence of phases that are there for a compiler, right? Now, in semantic analysis, what we do is that we have our syntax tree, okay, generated by our parser, and now what we want is we want to check for the semantics, right? Programming semantics. So what we do is we need to add some semantic rules, right? So now what we do is we add semantic rules. Now over here on your slide, what you can see is that the text in red color, okay, they are the rules that are specified, okay, the semantic rules. Now these semantic rules are described using some attributes, right? So now for the terminals and the non-terminals, mostly for non-terminals, okay, we will have some attributes. The terminals attributes, okay, they are defined by they are lexically defined, okay, in the previous stage. So its value is not going to change in using these rules, okay. But here the attributes whose value is going to change or it's going to be affected, okay, those attributes we are describing in the semantic rules. Now the attribute, if there is an attribute associated with your grammar, then that grammar is called attribute grammar, right? So now these attributes are divided into two categories. Okay, one is synthesized attribute and second one is inherited attribute. Now in your parse tree, okay, whenever any attribute is getting its value from its child node, when any nodes attribute, like say suppose in this diagram, if you see that the value of a dot count, okay, is getting its value based on its child node, how many A's are there, okay, accordingly we are deciding the count of A. If you look at one level above, okay, indicated by node number 4, right? So there you see that A dot count equals to 2. So how did we get the value 2? It was based on its children, right? So its value is synthesized from its children, right? So that is why such an attribute whose values depend on the children or it is synthesized from the child node, okay, those are synthesized attributes. Now, if it is the reverse case, right, that the child node is inheriting an attribute from the parent, then naturally that attribute is called inherited attribute. Right? Now, has got only if the grammar has got only synthesized attributes, right? There are no inherited attributes, then that grammar is known as synthesized grammar. Okay, so it is very significant. Okay, in the topic of compilers and more specifically semantic analysis, right? That we focus or give lot of emphasis on synthesized grammar. Okay, we will realize why it is important. Okay, now synthesized grammars, okay, they can be evaluated using the bottom up technique. Okay, so I think that in syntax analysis, okay, you have learned about bottom up approach, and also you are aware about what is top to bottom approach, okay, top down approach, right? So over here the attribute evaluation is done from bottom up, right? Why it is done bottom up? Because the parents uh, attribute is dependent on the child attribute. It is synthesized from the attributes of the children. Now over here, if a grammar is given to us, or maybe if a grammar is not given to us, simply a definition is given to us that you need to generate an attribute grammar for a certain condition. Okay, say suppose like over here, what condition we are satisfying? The number of A's, B's and C's should be equal and it should be greater than 1, right? So our grammar must have equal number of A's, B's and C's. So what we check is that if the count of A equals to count of B equals to count of C, then we say that the string is accepted by our grammar. Right. So for this is how we have defined the semantic rules. Okay. So with some practice and with some examples that we will discuss, you should be able to generate these semantic rules. Okay, for a given grammar. Okay. So how to write a grammar from a given definition, that I am sure that you are able to do. Okay, or you are learning how to do it. Right. Now you should also be able to decide that what semantic rules are to be associated with the grammar. Okay, what attributes we will need and how we will manipulate or work with its values. Okay, so I think this example is clear to all of us. Okay, except for the dependence edge that we will discuss in the next slide. So far, are you having any doubts regarding this particular example? So if the definition is given to you, okay, as we discussed in the previous class, you should be able to write a grammar and write the semantic rules. Now combination of this grammar and semantic rules, okay, it is known as syntax directed translation. So you may find in your reference material, okay, in your textbook, the name of the chapter as syntax directed translation, or in short it is known as SDT. Okay, so that is to be remembered. Okay, basically it is the same. This is the formal name given to this particular way of representation. Okay, so far are you having any doubts? Anybody? Then please let me know. Okay, otherwise I will continue with the next topic that we are supposed to discuss, that is dependence edge. Yes, examples we will discuss. Okay, lot of examples we will discuss for this topic. I am just talking about this particular example. Are you having any doubt in this example? We will be discussing minimum 5 to 6 examples, okay, related to this. Okay, fine. Mayank is not having any doubt and nobody else has written anything. I am safely assuming that you are all getting it. Okay. And if you are having a few doubts, okay, as we discuss few more examples, I am sure it will be clear to all of you. Okay. So now let us discuss the next thing, that is attribute dependence graph. Okay. Now let us look at the formal definition of it. Okay. Let T be a parse tree generated by context-free grammar of attribute grammar G. Okay. Now the attribute dependence graph, or we will also call it DG for short. Okay, dependence graph. Okay, we will not use the entire name because all the graphs that we are now going to discuss, okay, they will all have attributes. Okay, now we are working with semantic analysis, so we will have attributes, right? So dependence graph, okay, for this parse tree T. is a directed graph. Okay, now when it is a directed graph, naturally we will have two things, its vertices and edges. Now how its vertices and edges are defined, let us see. Now V is a set of B where B is an attribute instance of some tree node, right? So now every node, okay, will be some non-terminal. It will have some attribute, okay, and B is a set of all the attributes. Now that will form the vertices of the dependence graph and the edges. Now how these edges are going to be defined? Edges are defined between nodes, right? So if there is an edge between B and C, okay, then what is the meaning of it? B and C are the attributes of grammar symbols in the same production P of B, and B and the value of B is used for computing the value of C. Value of B is used for computing the value of C in attribute computation rule associated with the production P. Okay. Now from this, can you identify which one is the child node and which one is the parent node? The edge is from which node to which one? From B to C or C to B? From the definition, can you tell me? Value of B is used to compute value of C. So we are having an edge from B to C, right? So synthesized attribute, okay, as the definition we have discussed, okay. So the edge will be from B to C, okay. So I think now the formal definition is clear to all of us, okay. Now moving ahead. Now let us discuss some characteristics of this attribute dependence graph. The attribute grammar, okay, it has to be non-circular, okay. And what is our need? That the dependence graph is acyclic. If the dependence graph is cyclic, okay, then we will not be able to uh, find the values of the attributes, okay. We will not be able to describe our attribute grammar, okay. So it is necessary that this dependence graph is acyclic, okay. So non-circularity, okay, it is very expensive to determine, okay. So because it is exponentially proportional to the size of the grammar, right? So our interest will be in the subclasses of the attribute grammars whose non-circularity can be determined efficiently. Okay, so we will be considering only those attribute grammars, okay, for whom we can easily identify its non-circularity. Okay. Now assigning consistent values to the attribute instance, okay, in the dependence graph is the attribute evaluation. So how the attribute will be evaluated, okay, that we will see next. Okay, and this assigning values to the attributes, okay, it is known as attribute evaluation, right? And we will be doing it in, generally we will be doing it in bottom to top manner, okay, and mostly we will also be going about bottom to up and left to right, okay. We will see some examples wherein the grammar can be evaluated from top to bottom also, and it gives us the same answer, right? So let's see. Now, what is the attribute evaluation strategy? Means how this attribute is supposed to be evaluated. Okay, this is the formal steps. With practice, we can eliminate some steps. Okay, and we can obtain the answer directly. Okay, so let us try to understand that what is the exact procedure for attribute evaluation. First and foremost, we have to construct the parse tree. Now, all of you know what is parse tree and how it is supposed to be constructed for a particular language. Okay, you will describe the grammar and then for a given input, you will construct the parse tree. Now, from it, what you have to do is you need to construct the dependence graph. Now, what is dependence graph? That we have just discussed in the previous slide. Okay, so that we will construct. Then what we will do, we will perform topological sort on the dependence graph and obtain an evaluation order. Okay, so now what we have to do, we have to perform topological sort on the dependence graph and we will obtain evaluation order, right? Now from this evaluation, okay, or rather on the basis of this evaluation, what we will do is we will evaluate the attributes, right? And how we will evaluate the attributes? Using the corresponding attribute evaluation rules attached to the respective production. So in the first slide which we saw today, okay, the semantic rules, okay, they are with respect to different productions. Okay, they are corresponding to different productions. So that attribute evaluation rules we will use and we will evaluate the attribute. Multiple attributes at a node in a parse tree may result in that node to be visited multiple number of times. Okay, say suppose a particular node is having some synthesized attributes and some inherited attributes. Okay, both the type of attributes together is possible. Okay, the only thing which we mentioned in the last class, if you remember, is a particular attribute can be synthesized or it can be inherited. It cannot be both. But for a particular node, we can have multiple attributes, and all those attributes may be synthesized or may be inherited, okay, or a combination of those, right? So that is why each visit, okay, will result in evaluation of at least one attribute, and it is possible that a node is visited multiple number of times. Okay, it depends on the grammar. Okay, so this is our evaluation strategy. Now, very quickly, we will just go through this attribute evaluation algorithm. Okay. Even if we don't follow this algorithm line by line, okay, the technique of attribute evaluation is very simple. Okay. Because this is in the syllabus, I'm just going through it very quickly. Okay. Our input is going to be the parse tree with unevaluated attribute instance. Okay, and what we will get is we will get a parse tree with consistent attribute values. So we have to generate these attribute values. We have to evaluate the attributes. Now, how we are going to do it? Okay, we will take a queue. Okay, W is going to be a queue wherein we will put all our uh, vertices. We will put all our nodes, and we will put in those nodes whose in degree is 0. Okay, then what we will do is we will take a loop till all the nodes are considered. Okay, so our till our W is empty, what we will do is we will take the node from W. Okay, so initially there will be only one node, right? So basically first we will take one node, then we will find the value of it by appropriate attribute computation rule, right? And then what we will do is for all the edges, okay, B to C, okay, in the edge set, what we will do is we will decrement the in degree of C, and if the in degree of C becomes 0, then what we will do is we will add it into the queue. So what happens with this algorithm, that we will consider all the nodes till all the nodes attributes are evaluated. Okay, so this is how we will go about the evaluation of the attributes. Okay, so basically what is our aim? We will consider all the attributes for all the nodes. Once we are able to compute it, okay, then we can say from that evaluation whether a particular input, whether our string is accepted by the grammar or not, following the semantic rules. Okay, so moving further, now over here you can see that the dependence graph, okay, is shown by the red dotted line, okay, as we had mentioned in the previous class. So now over here, if we try to discuss that there are many evaluation orders possible, okay, but the technique that we are going to use, okay, for most of our examples is bottom to top, left to right. Okay, so here you can see that, see, if we evaluate node number 1, 2, 3, then 4, 5, 6, and then 7, okay, then also it is valid, because we wouldn't have any node, okay, being evaluated before its child node, right? Now second possible evaluation order, okay, which you can see over here is 2 3, then 6 5, then 1 4, then 7, okay. And you can also think of multiple evaluation orders, but okay, the order that we are going to use now is going to be of this sequence, okay, 1 4 2 5 3 6 and 7, okay. So what we do is our first order, the evaluation order will start from 1, okay. So what we are doing is a dot count equals to 1, then we will calculate a dot count at node number 4, okay. So what we have to do, we have to make use of the production a gives AA. Okay. So what our rule says that our A dot count plus 1 we have to do. Okay. So whatever is the value of A dot count, it is 1. We add 1 to it and hence the value becomes 2. Right. Then we move to the next node, okay, that we have to consider, that is node number 2. Okay. So now B dot count equals to 1, right? It has got only one child node B, right? Now we move up, okay, we are using bottom to up technique, okay. So now we check our node number 5 and now the B dot count becomes 2, right? 1 plus 1 equals to 2. Similarly for node number 3 and node number 6, right? Now we have evaluated 1 4 2 5 3 6. Now it is node number 7. Now what we have to do for node number 7, s dot equal. Now our attribute is equal. And what is our attribute evaluation rule? S dot is equals to true if a dot count equals to b dot count equals to c dot count. Right. So now we see that over here all the counts are equal to 2 and hence s dot equal is having the value true, otherwise the value is false. So what we are checking over here is, suppose our input is AABBCC, then it will be accepted by the grammar. Now say suppose if we are giving input A, B, B, C, C, okay, then it will not be accepted by our grammar because our A dot count will become 1, B dot count is 2, C dot count is 2, okay, they will not be equal and hence S dot equal will give us false. Following this, okay. So this is how we can check using the semantic rules, okay. So grammar plus semantic rules will give a syntax directed translation. Okay. So this is how the evaluation is done. So as I told you, syntax directed translation is the grammar plus the semantic rules associated for each production in the grammar. Okay. So now we will be using the term SDT very frequently. Okay, so what you have to understand is, if you are asked to construct SDT, it means that you have to construct the grammar, you have to construct the semantic rules, okay, and then for a particular input, okay, you have to check whether it is accepted by the grammar or not. Okay. So now we are now taking another example. Okay. First and foremost, you will write an attribute grammar for evaluation of real number from its bit string. Okay. So what you are supposed to do, you have to write a grammar, then you have to decide its semantic rules. Okay. Now, first and foremost, we will try to write a grammar, okay, for the evaluation of real number, okay, from its bit string representation. So now over here I am taking this example wherein 110 dot 101 in binary, okay, what is its decimal equivalent? Okay, so what is the real number equivalent? So we know that how we can convert binary to decimal, more specifically when we are having a binary number that has a dot. Okay, so now you can see on the slide that how it is evaluated. Okay, so binary to decimal conversion, okay, we know very well that 110 is its decimal equivalent is 6 and 101 is 5. Now if we are having dot in our binary number, okay, then this is how we are supposed to evaluate, right? So decimal value divided by 2 raised to number of bits, okay, for the right hand side component, that will be added, okay, to the left hand side decimal equivalent. Okay, so I'm sure that all of you are aware about this particular formula, right? So now what we want to do is we want to write an attribute grammar for this particular evaluation. So can you try to write an attribute grammar for this particular aim? Give it a try, okay, and then we will compare answers. Okay, so what you have to do is our starting symbol, okay, whatever you want to name it, N, S, okay, whatever, okay, you have to write productions such that ultimately our productions terminals are 0 and 1, okay, because your binary number, binary string, okay, will have only zeros and ones, right? So try to write a attribute grammar for it, okay, and once you are ready with it, please let me know. I'm asking this question with an assumption that you already know how to write a grammar for a given definition. If you are not comfortable with it, then I can directly give you the answer and explain how it is suitable for this particular aim. Okay, so whatever is the situation, please let me know. Okay, let us discuss the grammar for this particular aim. Okay, and let us see if okay, Mayank has started discussing the parse tree, okay, for the same aim. But before that, okay, what we must have is we should be able to write the grammar. Okay, if you are able to do it from the tree and then writing the grammar, I don't know what technique you use. Okay, but ideally from the grammar we derive its parse tree. Okay, so let us discuss one of the possible grammars for this particular aim of conversion of binary to decimal, okay, with decimal point. Okay, so now please have a look at the grammar that you are able to see on your screen. Okay, so from N we have L dot L. So now this L is a list or yes, L is a list of bits. Okay, so we have a list of bits, then we have a dot, then we have another list of bits. Okay, so that will form our bit string, right? So now what can be there in your list? List can have a bit, and another list of bits that follows it, okay, or it can simply have a bit, okay. And now what can be the value of bit can be either 0 or 1, okay. So now this is one grammar that we are taking into account, okay. Now let's try to write the semantic rules for it, okay. So now what we should do, okay, when we have such a production, okay, that we are trying to decide, okay, by writing the semantic rule. So what should be our action when a production is encountered, okay, what we are supposed to do, that action we are defining as semantic rule, okay. Now over here, looking at the grammar, you may have another question, okay, that can we take the production L2 BLB, instead of that, can we take a production L2 LB or B? Means list of bits we are representing, okay, so now it is bit following a list or list following a bit, okay. So now we will take both these grammars, okay, and we will also have a look at different techniques of writing semantic rules. As of now we are considering this particular attribute grammar, okay. So now let us see that what will be the attributes, okay, for the non-terminal, okay. So here we are having non-terminals N, L and B, okay. So now let us see that what we have as attributes, okay. So now over here you can see that attributes for N and B, okay, will be only the value, okay. So B will have some value 0 or 1, okay, and N will have some value, okay, which will be some real number. For simplicity, val attribute, okay, we are taking as real for both B and N, okay. And now for L, what we are taking is we are taking two attributes. One attribute is the value, val, and second attribute is the count. Count is number of bits. Okay, because all of you know that whenever we try to convert binary to decimal, okay, whenever we are converting numbers from one system to another, okay, count is quite significant, right? So now let us try to understand the semantic rules, the actions that are associated with each and every production. Okay, for simplicity, we will start from the last one. Okay, if the value, if the production is b to 1, okay, then value of b is 1. So b dot val equals to 1. That is the attribute value. If b to 0, then b dot val equals to 0. Right. So now from the input, okay, we are reducing, okay. So that is why if from the child node we are getting the attribute value of the parent, okay, then it is a synthesized attribute, okay. And as we have discussed previously, if we want to specify a synthesized attribute, then we use this notation, okay. Synthesized attributes of N, synthesized attributes of B, synthesized attributes of N, L, and so on, okay. And the attribute, okay, beside the attribute we write an arrow pointing upward, okay, and up arrow is shown, right. So if you mention that all the attributes are synthesized, then you can eliminate the notation that we are using with the arrow, okay. But if you still want to write it like this, okay, this is also a valid notation. Now if we have a production from L to B, then L dot count equals to 1 and L dot val equals to B dot val. Okay. Then if you have a production L to BL, okay, then you see over here we have added a suffix 1 just to separate out the left hand side and right hand side. Okay, so which value we are using to compute which value, okay. So if you want to separate it out, okay, that is why we are writing L and L1. Otherwise, the meaning is the same. We are still talking about some non-terminal L. Okay. So now for count attribute, what we will do is L dot count equals to L1 dot count plus 1 and L dot val equals to L1 dot val plus B dot val into 2 raised to L1 dot count. Okay, so this is what we have been using previously, okay, to compute the decimal equivalent, okay, of binary number. Okay, so that same formula we have used over here. Okay, and then for the production n to L dot L, what we have done is to separate out both these L's, okay, the left hand side and the right hand side. We are writing down L1 and L2, okay, and n dot val equals to L1 dot val plus L2 dot val divided by 2 raised to L2 dot count, okay. So this is our semantic rules. With practice, okay, understanding the question, understanding the aim, okay, you should be able to generate these semantic rules also. Okay, so you need not expect the grammar being given to you, okay, and also the semantic rules also will not be given to you. Those are to be generated, okay, when you are asked to generate an SDP. Okay. So now I think in this slide, whatever information is written regarding the attributes and what are the semantic rules for each production is clear to all of you. Is it clear? Bullet point notation. Okay, there we are. I'm answering Hetu's question. When we are writing AS of n, it means that synthesized attribute of n equals to synthesized attribute of b. It is well. So we are having well as a synthesized attribute. Okay, for n and b, and we are having two synthesized attributes, count and well. Okay, which belong to the domain of integer and real respectively for the non-terminal L. Okay. Um, Fine. Still, if you are not getting it, okay, anybody, then please let me know. If you understand the notations, then it will be very, very simple. Okay, see, this technique is not very difficult. Okay, once you understand, get a grip over it, okay, then solving the examples of STD are very, very simple. And I'd like to mention at this point that as far as gate examination is concerned, this topic is considered quite important, okay, from compiler design. There are questions at times asked from this, okay, related to attribute, related to SDT, okay. So understanding this topic will also help you if you are planning to appear for gate, or if you have already appeared gate previously, okay, then you will also realize that this is quite important. Fine. Moving ahead. So now what I have done is, for the example that we have taken into account, okay, I have generated the parse tree, okay, using the grammar, okay, using the productions that we have, okay. So now what we will do is we will evaluate the attributes. We will evaluate the attributes using the evaluation attribute evaluation strategy that we have just previously discussed. Okay, in simple terms, what we are going to do is we will start from bottom up, left to right. Okay, you have to simply remember this thing: bottom to top, left to right. Okay, then you will know that in which order the nodes are to be considered. Okay, and once we are at a particular node, all we have to do is that we have to look at the production, okay, and do the action. Okay, so now let's start the evaluation. Okay, so now our input is 110.101, right? So now we will place it, okay, at our leaf node, okay, right? So now we are beginning with the evaluation. Okay, so now which node will be first evaluated? This one, right? So now what we are doing is we are having a production of B21. Okay, so the action that we will perform, okay, is b dot val equals to 1. So we will evaluate the attribute val for b and assign it value as 1. Okay, this is what we have done by reduction. Okay, so I hope that this terminology is familiar to you, right? So now next node is this, right? So again we are having uh, a reduction from B to 1. Okay, so now B dot val equals to 1. Right. Now what will be the next node? We are going from bottom up, left to right. So now which is the next node that we will consider? It will be this, right? So now which production is to be taken into account? B20, right? And B dot val equals to 0. How did we get B dot val equals to 0? By taking into account the semantic rule, the action that we are supposed to perform when a particular production is reduced. Okay. Now what we will do, all the right hand side nodes, okay, for L is evaluated. So now what we will do is we will have this production, we will have this reduction from B to L. Okay, so now what we will do is L dot count equals to 1. As you can see on the slide, okay, the rule that we are applying is highlighted. Okay, so L dot count equals to 1 and L dot val equals to B dot val. What is B dot val? B dot val equals to 0. So that's why L dot val equals to 0. Right. So now taking the next node. Now over here, what reduction we are having? We are going to use this production rule L to BL. Okay, so now over here, if we are writing L to B dot L1, okay, then it makes our task very simple. L dot count equals to L1 dot count plus 1. What is L1 dot count? L1 dot count is 1, right? And we are adding 1 to it, so now L dot count equals to 2. Now L dot val is to be calculated using the semantic rule that we have defined. Okay, so L1 dot val is 0 plus B dot val into 2 raised to L1 dot count. So B dot val is 1, right? And L 2 raised to L1 dot count. So what is L1 dot count? It is 1, right? So 1 into 2 raised to 1, that gives us 2. So now L dot val is equals to 2. Okay, so far I'm sure all of you are following. Okay, so now what we have is we have to take into account the next production. Okay, that is L giving B to L. Okay, so now it is reduced to L. So we are calculating the attributes of L. L dot count equals to 3. How did we get L dot count equals to 3? L1 dot count is having value 2. We are adding 1 to it. So now L dot count becomes 3. L dot val, using the formula which you can see is clearly stated on your slide. Okay, we are having the value as 6. Okay, now which node we will consider next? We will consider dot. Okay, so for dot we will not do anything. Okay, because none of the production is satisfied. Okay, so we will take the next node. Okay, that is B. Are you? I hope that you are following the order. Okay, we have not constructed the dependence graph specifically. Okay, but I think that with the examples it will be very clear to you that what we have discussed in theory, that we are using in the examples. Okay, so now over here we are now having the value 1. Okay, and 1 is reduced to B, so B dot val equals to 1. Now next input is 0. 0 will be reduced to B. Okay, so now we are looking at the fourth production. Okay, so B dot val equals to 0. So as you can see on your slide, B dot val equals to 0. Now next input is 1. So 1 is reduced to B. Okay, so B dot val equals to 1. Okay, now taking, now what happens is now we are having reduction, right? So B is reduced to L. So we are now looking at the third rule. Okay, it is also highlighted on your screen. You can see. So L dot count equals to 1. L dot val equals to B dot val equals to 1. Okay, so the values are for that particular node. Okay, now we are having the reduction of BL to L. Okay, so what we have is L dot count equals to 2. How did we get this? L1 dot count is 1 plus 1 is 2, right? And using the formula that we have given as semantic rule for L dot val attribute, okay, what we have is 1 plus 0 into 2 raised to 1, okay, equals to 1. So now L dot val for this particular node is 1. Now again we are having a reduction, right? So L dot count. So whenever we are having any reduction, okay, we will have a look at the production, and what we will do is we will apply the action, we will apply the semantic rule. So L dot count equals to 3. How did we get it? L1 dot count, that is 2 plus 1 gives us 3. L dot val equals to, using the formula again, 1 plus 1 into 2 raised to 2. 2 raised to 2 is 4. 4 plus 1, 5. Right? So L1 dot val equals to 5. Okay. So whatever we have been using previously, theoretically, okay, however we were calculating, okay, binary to decimal, same thing we have done using our semantic rules. I'm sure you are able to realize this now. Okay. Now, last reduction to be performed to reach the root node, that is n. Okay, so now let's take that last step. So n dot val, okay, uh, equals to L1 dot val. So what is L1 dot val? It is 6 plus L2 dot val divided by 2 raised to L2 dot count. Okay, so what is L2 dot val? It is 5 divided by 2 raised to L2 dot count. So what is L2 dot count? It is again 3. Okay, our input, okay, L1 dot count and L2 dot count both are 3. Okay, but whatever is the case, right, we are just simply using our semantic rule, right? So 2 raised to 3. So simply perform this calculation and we have our answer as 6.625. Okay, which is the decimal equivalent or real number equivalent, okay, of the given input 110.101. So our SDT is ready for calculation of binary to decimal, and we have done an evaluation of the given input to generate the necessary output. So far, I hope all of you are getting this. Okay. So now whenever you write on paper, okay, I am taking the notes and highlighting them step by step because I'm giving a presentation right now to you. Okay, but when you are writing it in your books, okay, you can simply number the nodes that you are considering. Okay, so whichever node you have considered, you can just number them as 1, 2, 3, 4, okay, to represent your evaluation order. Right. So once again, I'm repeating the evaluation order that we have used over here is bottom up, left to right. This is how we have evaluated the attribute. Does any student have any doubt at any stage? Okay. Just going to give you 1 minute. Okay, and then we will take the next example. Okay. All right. So it's very good that all of you are getting this. So let's just take the next example. Actually, the next example is the same aim, but we are now going to use another attribute graph. Okay. Now, all of you are well aware, okay, and I'm sure all of you must be knowing that for a given aim, you can have more than one grammars which are valid. Okay. So for this one, we will now take into account another grammar, okay, and we will use slightly different technique, relatively easy technique to go about the computation. Okay, so if something like this is asked in the exam or you are supposed to do it, you can use any method of your choice. Okay. So now this is an easy method that I'm going to show it to you, right? So now let's see. Now can you identify what is the change in the grammar as compared to the previous one? In the production L2 BL or B, we are taking production L2. Yes, that is absolutely correct. This is left recursive. Okay, previous one was right recursive. Now this is a left recursive grammar. Very good. Okay, so now the concepts, okay, of grammars you are able to correlate with any given example. So that is really good. I'm sure all of you are able to do it, though you are not typing in the chat, right? So now let us see that how we are able to evaluate our input, okay, to generate our output using this particular attribute grammar. Okay. So now we are going to construct the SDT. So again over here, what we have is we will have same attributes. Okay. So synthesized attribute for n. Okay, sorry, there is a mistake in this slide. Actually, synthesized as attribute for N and B, we are considering it as well. Okay, and synthesized attribute for L, we will have two attributes, count and well. Okay, I'm just sorry about this one, so I will rectify it before I upload on the drive. Okay, this is not to be written over here; it is to be written on the above bullet. Okay, fine. Now let us consider the semantic rules. Okay. Now n giving L1 dot L. Okay. So all these rules of our grammar. Okay. Now let us try to understand the semantic rules or the actions that we are supposed to take. Okay. So if we are having a reduction from either 1 or 0 to B, right, then B dot well, that attribute will be affected. Okay. So it will be either 1 or 0 respectively. Right. Now if we are having a production L to B, okay, so means we are reducing from B to L, right? Then L dot count equals to 1 and L1 dot val equals to B dot val. So far it is the same. Now comes the easy technique. Okay. If we are having a reduction from LB to L, okay, means we are having this production L to L1B. Then count of L1 plus 1 gives us count of L. Okay, so up to that much is okay as we have discussed previously. Now comes the easy part. L1 dot val, L dot val equals to L1 dot val into 2 plus B dot val. Okay, so now here we are simplifying, okay, the calculation of binary to decimal. Okay, so here we are using an easy technique. Okay, so now we are moving to the first production. Okay, N2 L1 dot L2. Here it remains the same as we have seen previously. Okay, so now let us use this grammar and the semantic rules. So basically, let us use this STD to generate the output for our given input. Okay, so I hope that this is clear to everybody, right? And there is no doubt so far. So let us try to evaluate the example. And I hope that in next 5 to 7 minutes before the lecture gets over, we are able to trace this particular example. Otherwise, at 1:30 we will continue. Okay, so let us try to focus. Okay, so now for our given grammar, we have generated the parse tree, right, for our input. Okay, we will be considering the same input as we have taken in the previous example, and we will check whether we are getting the same answer or not. Okay, so now our input is 110.101, right? And as we have correctly identified that this grammar is left recursive, okay, so you can identify it from the parse tree also, right? So parse tree is generated accordingly. Now 1 is reduced to B. So B dot val equals to 1. What will be the next reduction? B to L. Okay. So now the third rule will be applied. So we are reducing B to L. So L dot count equals to 1 and L dot val equals to B dot val, which is equals to 1. Now, which will be the next node? It will be, we will take the next reduction as 1 to B. Okay, so B dot val equals to 1. Now, what will be the next reduction? LB to L. Okay, so LB to L will satisfy this particular production L2 L1B. So now what we are supposed to do? L dot count equals to L1 dot count plus 1 is equals to 2 and L dot val equals to L1 dot val. What is it? It is 1 into 2 plus 1. So we have answer as 3. Right? So as such, you can understand that if our input in binary is 1, 1, then its decimal equivalent is 3. Okay, so far we are going correct. Right, so L dot val equals to 3. That is what we have obtained. Right, so our formula is correct. Now next reduction, okay, from our input, we are now having input as 0. So now next reduction is 0 to B. Right, so B dot val equals to 0. Now next what we will have is LB to L. Okay, so now again we will be making use of the second production and its associated action, that is L dot count is equals to 2 plus 1 equals to 3. L dot val, again using the formula, L1 dot val, it is equals to 3 into 2, 2 3 the 6 plus 0, 6. Okay, so now again you can observe that 110, its decimal equivalent, okay, 110 in binaries, its decimal equivalent is 6. So far we are getting the answer. So now we are sure, okay, that what we have implemented is absolutely correct. Okay, so now moving ahead, right, now next node will be dot, okay, that we will not consider. Okay, and if you have understood how the stack plays a role, right, then zero dot will be pushed onto the stack. Okay, I'm not going into that detail. Okay, it is not required over here right now. Okay, but you can understand it, right? So now what is the next input? Next input is 1, right? So we are having a reduction from 1 to B. So B dot val equals to 1. We are having next reduction from B to L. So L dot count equals to 1, L dot val equals to 1. Okay, L dot val equals to B dot val equals to 1. Right. Now, what is our next? Next input is 0. So what we will have is 0 is reduced to B, B dot val equals to 0, right? Now next reduction will be LB to L, okay? So we will calculate L dot count using the formula L1 dot count plus 1, so 1 plus 1, 2, and L dot val equals to L1 dot val into 2, so 1 into 2 plus 0, right? So we have 2. So again you can check over here, if your input is 1 0, its decimal equivalent is 2, right? Moving further, next input is 1, right? 1 is reduced to B, B dot val equals to 1, right? Now next reduction is LB to L. Okay, so L dot count equals to 3, L dot val equals to 5. Okay, so now last step is remaining. Okay, the last reduction to do, L1 dot L2, right? That gives us N. So N dot val equals to 6 plus 5 divided by 2 raised to 3. Okay, that is 5 by 8. So 5 by 8 gives us 0.625, and adding 6 to it will give us the final answer 6.625. That is the decimal equivalent of the input 110.101. Right. So finally n dot val we have obtained. So far I am sure you are able to understand. Okay, so from what we have discussed in this lecture, okay, is you should be able to construct the grammar, you should be able to construct the semantic rules, and You should be able to evaluate the attributes to generate the output. Okay. So we will take further examples in the next class at 1:30 today. Okay. So if you have any doubts, right, then we will discuss it in the beginning of the lecture and then continue with the example. Okay, so now I am going to stop the presentation. Okay, and if you don't have any doubts, okay, then I can safely sign out from the meeting.
Good morning all. In the last lecture we discussed regarding to image compression. We know that we are using it we need the image compression for two reasons. We want to transmit our image so that we want to save our bandwidth, and we want to store it, so we want to save our storage space. That's why we need image compression. Right, two type of compressions are there: lossless and lossy. Lossless will result into so if it is a lossless compression, that means if you will compress your image and you will go back by decompression, you are going to get your original image back. And if it is lossy, then you are going to get approximation of the original image, right? And what we also discussed, what are the advantages and disadvantages. That advantages of lossless is it preserves the information, but disadvantages, you cannot compress more than certain amount. And same way for the lossy, the what is it? You are not preserving the information. We are losing some information, but compression ratio will be higher, right? We understood the difference of data and information. The data, same amount of information can be represented by various amount of data. This is very much important again. That compression ratio is B divided by B dash. That is B is my B is my older or actual image or actual statement or whatever your actual data, uncompressed data, divided by B dash, which is a compressed data. Okay, and so redundancy is given by 1 minus 1 by C, where C is your compression ratio, that is given by B by B dash. What is this? That how much redundant data that you had. Then we studied about three different redundancies, right? Coding redundancy, spatial redundancy, and irrelevant information. Irrelevant information is that our eyes are not capable enough to distinguish between all the intensities. That's why you are simply ignoring or removing irrelevant information to your eyes. Spatial redundancy is that if your intensities are uh, common, so here in this entire row the information is common, so you can represent it using instead of representing individual information because they are related information with each other. Instead, so you will remove this partial redundancy or temporal information, and you will compress this information because pixels are row pixels are what we can say are related with each other. And coding redundancy is that all the symbols are not equally likely to occur. That's why some pixels are uh, what we can say, some intensities are occurring more frequently than others. So instead of having fixed length coding, we want to go for variable length coding. That means if my symbol occurs with more more frequency, I will associate less more frequency. If my symbol occurs with more frequency, that is, it is frequently occurring symbol, then associate less bits with that. And if the symbol is occurring less frequently, then associate larger bits with that, so that compression can be achieved. So then variable length coding is applied instead of fixed length coding. Here run length encoding is applied. What is run length encoding? So run length encoding is given by uh, the symbol and the count. The symbol and the count. That is, so run of the symbols is calculated. Okay. So one so okay, so that is fine. Now then we are also took that what is entropy. The equation of entropy is given by this. What is the significance of this? This proof we have already taken, so I'm not going to take that proof again. What is the significance of this entropy? It says that um, this much so here, because it is unit 2, it is base 2, so the unit is bits. So what it says, in each pixel this much bit information is stored, or each pixel contains this much unit of information, right? So in earlier, if so this entropy was calculated based on this example. If you can recall, it was calculated for this example, right? So what was the earlier case? Like earlier, 8 bit were used. Suppose we are not using the variable length encoding, like here variable length of code is used. Suppose I am using the fixed length code like this, right? So what was the required amount of uh, 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 what was my required amount of information? Suppose this 4 bit I want to transmit. So how many bits I need to transmit? Or suppose this 4 intensities I want to transmit, and if I'm using the fixed length coding, then how many bits I'm going to transmit? So I'm going to transmit this 8 plus 8 plus 8 and plus 8, right? Suppose I am having m cross n image, right? Suppose I'm having m cross n image. It is composed of these 4 intensities only, and I'm using fixed length coding. Then what will be the size, or what will be my number of bits that I will transmit? That will be m cross n into 8, right? My image size is m cross n, and it has these symbols, 4 symbols. Others are not occurring in my image. These 4 only are occurring, but I am using fixed length code. So this is what actually, not C, but this many bits I am going to transmit. Okay. But actually, if you will actually see what is entropy, entropy is 1.66. The entropy is 1.66. What is the meaning of that? Information contained in each pixel is just 2 bits. That means for each pixel you need to represent this 1.66 bits only. right? So suppose if you have m cross n pixel, how many bits you need actually? Suppose you have n cross n pixels, then actually you need 1.66. That much only, that much information only you have. That is the meaning. In each pixel you have how much information? The information you have 1.6614 only, right? And what exactly you are using? You are using 8 bits per pixel. That means you are using m cross n, and per pixel you are using 8 bits, but it contains information of 1.66 only. So what will be the compression ratio ideally you should achieve? So ideally at max you can achieve how much compression ratio? So we can say you can have compression ratio like, if you are not doing anything, then this is the way, and if you can do compress, then you can have this new bits, right? Why? Because if you will compress more, this is the ideal case. This is the ideal case. In my pixel, this much unit of information is there. So I cannot use lesser than this. I have to use this many bits per pixel. So this is the ideal case. Now what is my requirement? So whatever it is, so it will be 8 divided by 1.6614. This will be my ideal compression ratio. Okay. But now what is my requirement? I am using uh, right, I am using this type of coding technique. I am using this type of coding technique. Using that type of coding technique, I achieved average length of 1.81 bits. What is the meaning of that? Per pixel, I am now by using this type of coding scheme. Now I've reduced my number of bits per pixel to 1.81. What is the ideal requirement? My ideal requirement is, my entropy says that I will have 1.66 bits per pixel, but so this is my ideal one, right? But now I will need some coding technique so that I can reduce my number of bits per pixel. So I use this type of coding technique, right? By applying this coding technique, what I achieve this many bits per pixel, right? And what compression ratio I achieve? 8 divided by 1.81, which is of course smaller than 8 divided by 1.66. It is of course smaller than 8 divided by 1 point. This is the ideal one. I wanted to reach here. That's why I want, by reducing this, by reducing this 8, I wanted to reach here, and I wanted to get my compression ratio like ideal one. That's why I use this type of coding technique, and I could reach here, and which is of course nearer to the ideal one, but of course it is not the ideal one, right? So now what is our aim? Our aim is to get different coding techniques such that we can get variable length code, such that our average bit length is equal to so that our compression ratio in short becomes the ideal one. Our average length reduces to such that it matches our entropy. So this is the entire concept of entropy. Okay, any doubt in this entropy concept? Okay, so now all of you quickly calculate the entropy for this. Now see, now we have so many mathematical examples. So now you must have calculators with you, right? And if it will be like, if I will simply explain you and you will listen, you will not be able to clear. So now what will be the approach? I will explain you the scheme, then I will expect you that you will calculate the example and you will give me the results, right? So so now this is my image. Now calculate entropy for this. Calculate entropy of this. What is the meaning of that? Per pixel, how much bits are required? Here actually it is 8-bit image, right? So what I want to check actually how many bits I should give per pixel so that it is sufficient for, or it will convey the entire information. I want to know about ideal compression ratio. Then I will go for some scheme, and then I will check whether I am getting the ideal compression ratio. If not, then am I reaching to nearer to that? And if yes, that's fine. Otherwise, I have to go for something else, some other coding technique I need to go for. So you have to find out entropy for this image. What is the equation of entropy? Entropy's equation is probability of occurrence of intensity. This is a probability of occurrence of intensity. So that is what you have to calculate first, probability of occurrence of intensity, and that you have to take with the log 2 basis, and the same thing you will multiply it and you will repeat it for the all possible intensities. You will take negative sign of it, right? So first of all you will need here is probability of occurrence of different intensities. Then take that, multiply it with the same one, but take log to the base 2. Sum it for all the possible intensities and take a negative sign here. Of course, this is remaining. We are coming here to this. Now calculate probability of 21. Then calculate probability of 95. Then probability of 69. And probability of 243. Right? And so that will be your different p values. Then take p into log p to the base 2, summation for all intensities. So some only 4 intensities are there, so summation of this 4, and take minus sign of that. Quickly give me this result. First tell me what is probability for 21. Give me p21 value first, then give me p95 value, p169 value, and then p243 value. I'm waiting for your answer. Quickly calculate and let me know. What is p21? P21 is 0.375. 0.375. Okay, it is 0.375. Okay, so the answer is 0.125, 0.125, 0.375. Okay, so I'm writing that directly here. 125. Okay, that is 0.125. No, 0.375. Okay, so these values are with us now. Okay, good. So we have these values. Now take that probability to take log to the base 2, multiply with the same probability, like 0.375 log 0.375 to the base 2, and do for all 4 and sum them up and take negative sign because this is point values, so less than 1 values, that's why negative sign is going to be needed, so it will negate the negative sign. So final answer comes 1.8. Final answer comes, it is 1.8. So this is that equation. Actually, ideally you should go for all 255 values, but here only 4 values are there. That's why we are going for the 4. Ideally, you should check for all the possible intensities. So it is, yes, it is your result. So you just verify whether you are getting the similar uh, answers or not. So it is 1.81. So what is the meaning here? That ideally I should compress such a way that my average length should be 1.81 around. It should be 1.81, near to 1.81. Okay. So this example we will use multiple times. So just keep this results in your mind. Any doubt regarding to this, please ask, because this is very much important example for now. So now whatever coding technique I should apply now, then it should result into average length such that it will be near to this. If it is far from this, that means it is not a best compression or it is not a good compression. 1.811. Okay, so this is all about entropy. Right now, if you remember variable, so entropy I think is revised and it is very much useful concept. So now we will need it, but now let us discuss one more point regarding to run length coding. Okay, before we go to run length coding, let's just complete this variable length coding. Can anyone answer this? That can variable length coding procedure be used to compressed histogram equalized image? Suppose I have one image and I apply histogram equalization to that. Can I use variable length coding procedure to compress that image? You cannot apply this. What is the reason? What do you think? Why we cannot apply? Answer is correct that we cannot apply variable length coding to compress histogram equalized image. Why so? What can be the reason? Yes, here what will happen that all the intensities will occur with equal probability. So there will not be any. So there will not be any intensity which is almost equal intensity will be there. So there will not be like this intensity is occurring most more probable. It is more probable than others. So that's why variable length coding procedure cannot be used or it is not suitable enough for histogram equalized image because all the intensities are occurring there are having almost equal probability. So whom to assign what type of code? So suppose I am assigning a fixed code n to all, then it is not a variable length coding. I have to, because they are equal probable, I have to assign equal length code to all, right? And that is not that variable length. So can I apply spatial or temporal redundancy methods to remove spatial or temporal redundancies to such images? Can we apply or can such image have spatial or temporal redundancies? Can histogram equalized image have spatial or temporal redundancies? Yes, a histogram equalized image can have temporal or spatial redundancies, right? Why? So if you will see here, this is also good contrast image. It is having equalized histogram. It is having equalized histogram, right? But it is equalized histogram, but it is a good contrast image, and it is having spatial redundancy. So histogram equalized image, you can apply any method which removes partial redundancy. It may remove that irrelevant information. You may remove, right? But what you cannot apply is variable length coding is not you cannot apply for that. Now for the spatial and temporal redundancy, what we are using run length coding. We are using run length coding, right? Okay. So can run length coding be beneficial for every image?
Take three example. What is run length coding? What generally a run length coding says? Here I will count that this is 1, 2, 3, 4, 5, all these pixels. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? These are 10 pixels. Then 20 and 23. 23 like this. Suppose I am going like this, then this. So 23 consecutive pixels are having white value. So what will be my, so I will say white has 23, then 1, 2, 3, 4, 4 are having black, so on. This is how I am going to, this is what my run length coding is, right? Now check for this and check for run length coding for this. Can I apply run length coding or is run length coding beneficial for all kind of images? What will be the case here? Yes, what will be the problem here? What will it compress? So here what actually we will need it that black 1, white 1, black
1. So what happened actually, for 1 byte, I actually needed 2 byte. For 1 byte, actually this expanded my image. I wanted compression. Here it was fine that 23 pixels consecutively were having white color, and hence I just needed 2 bytes to for this 23 bytes, and it worked well, right? But here what will happen, per pixel I need 2 bytes. So earlier whatever the size was, now it is a double size. So run length coding is not necessarily useful for all, but it is highly used in most of the time BMP images, right? It is used in BMP images, that bitmap images. Okay, what about this? Assume this is 1 pixel thick only. Assume this is 1 pixel thick only. This is 1 pixel, second pixel, third pixel, fourth pixel. Can I apply run length coding here? Assume this is 1 pixel thick only. This is 1 pixel, then next pixel, then 1 pixel, again the next pixel, like this. I hope you can understand it now. Think, Jamin, or all of, yes, that is what the idea is. Yes, Priyal, we can go with that. So, what is the case like run length coding? As if we are going with Jamin or Mayank, so why they said no? The reason is they thought like yes, yes, that's true, Vivek. So what was their idea, that they were just going horizontally, right? Yes, yes, true. I understood. So what is the case like if it is we are going with the horizontal run length coding? Then of course it is not suitable, right? So, but variants of run length coding, some variant we can have, and if it is we are going with that, then it is possible. What is that variant? Variant is that I will encode it vertically like this, right? I will encode it vertically, right? So, what is the case? What is my point here? It is not like run length coding is like just you have to scan horizontally. So many variants of run length coding are available, right? The point is that you should know and your receiver should know which variant is used. That type of protocol you can have initially decided, right? So if you are going for the vertical type of run length coding, then it is fine and it will successfully work here. But definitely, if I will go with the horizontal one, it is not going to help. So you can have so here what is our point? We can have multiple variants of run length coding. One of them is scan horizontally. Second one is scan horizontally, but how you can scan like this? Scan like this, then scan like this, then scan like this again. Not in zigzag pattern. First you can scan in this way, then you scan in this way, then you scan in this way. Instead of scanning in this pattern, right? You can scan in this way as well, right? Yes, Mike, we are coming to that point. Next point is this is one kind of variance. This is second kind of variance. Third is you can go with the vertical one, right? Sometimes it is also just how it is encoded, just row wise it is encoded. Like instead of encoding 23 pixel consecutively, it is also possible that you can have white 10, then again white 10. So this is also one variance of run length coding. You are just encoding rows. You are not considering them consecutive entire vector. You are not considering image as a vector or consecutive pixels. Just one row is encoded using run length coding. The next row is encoded using run length coding. That is also one possible variance of run length encoding, right? So here what Mayank says that we will be able to compress it, but we have to store which variants we have used, right? Suppose I want that flexibility that any kind of variance you can use, then you can have symbol that if I will send you 0 first, that means it is one kind of variant. If I will send you first 1, then it is first kind of variant. That kind of understanding you can have with your receiver, right? And if you fix for certain kind any variance you are fixing with your receiver, that I will always encode vertically, then you don't need to store it at all. Understood? So here, what is the whatever kind of coding you are using, but the point is your receiver should be able to decode it originally. It should be receiver should be able to understand. That's it. Whatever the way, whether you are conveying it to your receiver, whether you have predefined understandings, whatever it is, right? So that depends at what kind of flexibility you need. Okay. So that is all about this example. Now we are going for the fidelity criteria. What is that fidelity criteria? We have discussed already that suppose I am compressing my image, right? I am compressing my image. So I had my image, then I had some compression, and then for the it's like this. I can show you this diagram will help us again. Okay. So I have my image, I have compact information. Now I am decompressing it and I am getting approximation of my original image. I am calling it as f head and I am calling it as f, right? I am calling this as f head and I am calling this as f. So if I am, of course, this is approximation, so it is not exactly like this. So I can get f head minus f. So I am going to get some difference, right? And that is what known as error. Right? But I want absolute value of error so that I can sum up and I can get the cumulative error. If I will not go for the absolute value of it, what will happen? Some positive error, some negative error will cancel each other. And I will feel, okay, it is a very less error or zero error, but it is not the case, right? Possibly somewhere this is higher than this, somewhere this is higher than this. So I don't want that, I don't want to go in the sign part, I want to take the absolute value. I can take absolute value or I can take square of it, right? Okay. But what I want, I don't want to just know about the total of error. I want to know what is average error. So I will take square of it so that I can get absolute idea of the error. And then I will go with the, I will repeat it for all the pixels. So totally if my image size is m cross n. So I will have such m cross n differences for this pixel and this pixel difference such a way m cross n pixel differences I am going to have. Such m cross n error values I am going to have. So if I want to know about average error, what is average error in my image? So I will come to know about 1 divided by, I will have to take it division with the total number of errors. So it will be mn. But I have taken here square, so I want to nullify that square. So I am going to take square root of that. So this is nothing but RMS root, mean, and square. Root, mean, square, or you know that square you need to take square first, then mean, and then root. So this is known as RMS of your error, and that is what my fidelity criteria is. Fidelity is what that how your approximation, how close your approximation is to the original. That is fidelity, right? So, so if error is lesser, that means my approximation is near to original. And that's why this is objective way to identify your fidelity, right? Your system is said to be more, it has more fidelity if your error is lesser, right? So this is where what your, that is what just we discussed, root mean square. It is actually the idea of average error, right? And then same way, what is SNR? SNR is signal to noise ratio. What is signal? Signal is your image, your approximation, right? So your signal power or your approximation power is taken by your image intensity square and summation for all the possible locations. So whatever your image of m cross n size is there, this is your approximation, right? This is your f head. So for each location I am going to take the value, I will square it. The next location I will take, I will square it. I will repeat for all m cross n location, and in the denominator we will keep the error. So this is actually, error is noise for us. It is unwanted part in our image. So actually we got this signal and divide by the error. This is error, if you can see, right? Error square. So these two are different, we can say, uh, here this different metrics we can say to identify the fidelity. Here you understood if error will be less, if my approximation will be, if my approximation will be closer to my my original image, then the summation and then nth average and square root of it is going to be lesser. Same way here, if this will be near to this, then this difference is going to be lesser, and hence signal to noise ratio is going to be higher. So if this is higher or if this is lesser, my fidelity is good. And this is what objective fidelity criteria. Here you don't need anyone's help here, just mathematically you can apply. You don't need any subjective help or from any expert advice. You don't need here, just you have to substitute the values you are getting, and whatever answers you get from based on that, you can easily decide whether the fidelity is good or not, right? But there is one more subjective fidelity criteria is there. So what I will tell you, what will happen here in subjective fidelity criteria, we will have our image, we'll compress it, and we will decompress it, and we will get the approximation. Now I will show you the approximation. You are now then I will take that subjective idea from the humans, the experts. I can decompress it, and I can show you 10 10 from you. I can show it that to 10, any 10 students from you, right? And you may, some of you may say, okay, it is excellent image, it is very near, it is extremely good quality, it is as near to as my original image. Some of you may say, okay, fine. So suppose I have shown to 10 students, and out of 10, 8 said that it is excellent, it is excellent decompression. That means my decompressed image is very similar to, very near to original. Then I will say, okay, my compression technique is good, right? So if I want to check my compression technique is good or not, I have two methods. What are they? One is objective. So what I will do, I will use my compression technique, and I will decompress it, and I will obtain this value, and then I will find out RMS, I will find out SNR, and then I will check the values whether it is less or not, or whatever, right? And based on that, I will decide if error is less, that means my compression technique is good. That is one way. Second way is you can go to human subjects, and you can ask them whether the what is the condition, what how it look, what is the condition of my approximated image. So you may have multiple outputs. You may have, some may say it is excellent. Sometimes you may get that it is inferior quality. Sometimes it can be unusable quality, right? Sometimes it can be marginal, that it is of that okay type quality, passable quality, right? So this type of metrics you can have, this type of object, the valuations you can do here, right? So some of you say, okay, but this is not a good idea, right? Because it is very subjective, and we have to. So this is not a good method to check. Yes, I agree, because it is subjective. So generally, this is not taken. But in certain scenarios, it is preferable even. Like here, if you will see in this image, if you will see, this is the image, original image, right? And this was the result of compression and decompression of technique 1, and here the compression and decompression of technique 2, right? Here, if you will see carefully, because of this zigzag and all those things, because of this zigzags and all this you observe, and here you also observe this 1 and 2, this two thing you just observe. Now let's go with the subjective fidelity criteria. This is my original image. This is the result of compression and decompression of by technique 1, and this is the result of compression and decompression by technique 2. Let's go with the subjective fidelity criteria. Rate this 1 and 2 quickly. Rate this 1 and 2. Which one is suitable for you? Which we should continue with? Which technique we should continue with? 1 or 2? Yes, you many. Yes, 1. Yes, 1. That's so. Yes, so see here it was very easy for you. So this was, so yes, you will go with this technique, right? Now, um, so what the subjective fidelity criteria says, that this is more suitable. This technique is more suitable. That is what just we applied. Subjective fidelity criteria we just applied, right? Now, if we will go with this type of ERMS and SNR, actually, if you will compute for both of them, because if you will observe here, this extra distortion, if you can see here, you can see this is very high noise compared to the noise here. compared to the noise here. Observe, right? Observe the noise. Compare it with the original. See, if you will compare this portion, and this portion of 3, right? What objective criteria will say? In this image, this is if this is original, then here the error is lesser. Because here, if you will see, everywhere there is a noise. So if you will go with the objective fidelity criteria, this will give us the poor result than this. But if you will go with the subjective criteria, this is definitely not acceptable one. Though it is having noise here, but this is acceptable when at least it contains everything. Here some information is missing. So this is not at all acceptable. But because we are just going for noise here, unwanted information, here a lot of unwanted information is there. Right? And that's why objective fidelity criteria is going to give the result that this one is better than this. Right? So it is not like say every time only objective fidelity criteria is good. Okay, but of course for us, for our case, what we have to go with, for our case we will just check with objective one, but you should not underestimate the subjective fidelity criteria as well. It is also very much important. Okay, so this is the problem with the objective fidelity criteria, that if uh, uh, it is having noise like this, though it contains every information, because of noise, it will give us non-acceptable results. Okay, now let's go with one example. Let's go with one more example. What it says. So here we want to understand that RMS and all those things that we want to discuss, that we have already discussed, that ERMS and SNR, right? That we want to check for this example. What it says. Uh, mm, so intensity 8 pixel line. So there is one line, this line that you want to compress, right? This line you want to compress, and what you have to do, you have to quantize it with 4-bit accuracy, and then you have to compute by, if you quantize it with 4-bit accuracy, then you have to compute the RMS error and signal to noise ratio for this quantized data, right? So what I have to do, this is 8-bit representation of certain information. This is for every intensity I am using just 8 bits, right? Then I want to quantize it to 4 bits. I want to convert this 8-bit to 4-bit. Okay, and so if I will convert to 4-bit, definitely I'm going to lose some data, because quantization loses the data every time, right? So we are going to lose some data. So that data, so what is the data loss? So so if I will quantize, so I'm going to get f hat, then I will get RMS error. What is RMS error? So f hat minus f, square of it. For all I will do that, then I will sum them up, then I will divide them with total, right? Total, whatever the total is, 1 2 3 4 5 6 7 8, so totally are 8. I'm going to divide it with 8, so this is my mean, and then I will take root. So square, mean, root means square, right? Now only the question remains how to change this 8-bit to 4-bit. So this is my 108, say, or 139. I can represent it into 8 bits like this, right? This is 8-bit representation of 108. This is 8-bit representation of 8-bit representation of 39, 139, right? Now I will convert it into, I have to convert it into 4 bits. Now how to convert it into 4-bit? Many other methods are there, but simplest method is that, what I want to convert this 8-bit to 4. Should I use LSB 4 bits or MSB 4 bits? If I want to, just I have to suppress 4 bits. Should I suppress LSB or should I suppress MSB? most significant bits I should suppress, or I should suppress least significant bits. So I mean I should keep MSB, or I should, yes, I should keep MSB and I should suppress LSB, right? I should suppress LSB and I should keep MSB. So I am going to suppress them here. So this is what I am storing: 0, 1, 1, 0. Of course, I have to store most significant bit. Otherwise, least significant bit is having least information there, right? So I should suppress least significant bits. So this is what I will store. This is what I will store. 1000. That is 100. That is what I am going to store. Right. So this is how it is storage. So this is my original image. This is compression. Compression occurred. Now when you retrieve, you have to decompress. How will you decompress? So this is your value? No, this is not your value. This is just 4 bit. How will you get your remaining 4 bits? Remaining 4 bits you are going to fill with zeros. This is how you are going to decompress. This is what the decompression is. This is what your decompression is. Original image, this is compression. You just quantize it to 4 bits. This is your 4 bits. These are your 4 bits. So this is how it is stored in your system. Here you can see that. Here it is. This is how it can be stored. Here it is how stored. Now you have to retrieve. So you have to decompress. So now the value stored is 1000, but it is just 4 bit. I know my representation was of 8 bit. So how I will fill rest 4? I'm going to pad with zeros, 4 zeros, right? So if I will pad with 4 zeros here, if I will, okay, so if the intensity, so definitely you are going to, if you are considering the MSB, then you have to store 0000, and that is how you are losing the information, right? If the intensities are included 1, 2, 3, 4, so you have to store 0. That's it. Okay. So if your scheme is to store MSB and if 8-bit representation is there, right? So what you will store? You are going to store 4 zeros, and when you will retrieve, you are going to add again 4 zeros, and that is so now suppose it was 8. It was 8. Now you retrieve, then it will become 0. Then loss will be of 8. Okay. We see here we are achieving the compression of 4 bit. It is 50% compression. It is very high compression, so definitely loss is going to be very high. We are doing this 50% compression by lossy method of quantization. So you can understand here the loss will be very high. So definitely it is going to be uh, uh, it is going to be lossy, and loss, the amount of loss that just we will see now, that you will see here. You will understand here what will be the loss, right? See now, suppose so this is what I will retry. What is that? If you will see, it is equivalent to what it will be: 0, 1, 2, 3, 4, 5, 32 plus 64, right? 32 plus 64, that is 96. So it is equivalent to 96. So what I will retrieve is 96, what actually value was of 108. So this is my f of xy. F cap of xy is 96. So what is the loss? 96 minus 108, that is what the loss is. Okay. So that way I obtain. So here what I will get as a loss will be of 96 minus 108. That is what is the loss? Loss will be of minus 12. Right? Same way for 139, what will be the loss? Give me the loss for 139, 135, 224 quickly. Give me the, I hope you are getting the point, right? Are you comfortable with? So now give me the loss for different, so what I want to compute f hat minus f for all possible intensities. then I will sum them up, square them, then I will sum them up, then I will take its average, and then I will take square root. That is how I will obtain RMS error. So give me loss for all other intensities. For 139, for 139 it is minus 45. For 139 it is minus 45. Geta, please check. I don't think that loss will be of minus 45. Minus 11 for 139, because see, actually it is 4 zeros. If I will add here, it will be 128. 128 minus 139 is going to be 11. Yes, you should. You have to take for you have to take for every intensity here. So quickly do that for all. For 135, anyone has calculated what it will be? Yes, it will be 7 minus 7 for 135. For 244, if anyone is ready. 4. Okay. Then go for the next. Minus 12. Minus 13. Minus 8. And minus 3. Okay. So this is what f minus f f hat minus f we obtain. Now what you have to do? You have to square all. You have to square all, right? You have to square all and sum them up and take its average. You should take average of squares. First you square them and keep that in a side, because in SNR you will need. So first you take them and square it and keep that square value in a side, because it will be needed here as well as here. Then you take average. So this different square, the square of these differences and summation of it is needed in two equations. So what is your summation of these squares? Summation of the squares? 572. 572 is summation, and then average is divided by 8. Average will be 8 only. 1, 2, 3, 4, 5, 6, 7, 8. And square root of it. So what is ERMS for your case? The square root of 572 by 8. So give me the value of ERMS. 8.456. 716 is the answer. Okay. Summation is 716, not 572. Summation is 716. Okay, yes. So summation is 716. Real, please check. It is 716. Okay. Multiple answers are coming 716. So please check. Okay, if it is 716, then again, what is RMS? What is ERMS? ERMS is 26.75. So what you have to do? This is just your summation of squares. You have to divide it by 8 and then you have to take square root. Rutvik. 9 point, Nidhi, or 9, it is 9 point, yeah? 9.46. Okay, so yes, it is 9.46. So what you have to do? 716 divide by 8 and square root of it. Okay. So that is, it seems like it is coming like 9.46. Okay. And that is what our ERMS is. Fine. 9.46 is our ERMS. What about a signal to noise ratio? What about signal to noise ratio? So what, how to obtain it? So equation wise we can check. What you have to do, whatever your F hat is, you have to take a square, and whatever summation you had, that 716, you have to divide it with. The only thing remaining is your this values. I hope you have stored them. That here you were having 96. Here you had 128. That was the F hat value, na? From which you take the subtraction. So you have to take 96 square plus 128 square and so on. You have to take square of all those values and summation of. I hope you have stored those values. You have that those values with you. And do that and give me the SNR value. If not, then you can subtract it from this and you can get your idea. 96 minus 3, that is 96 must be your F hat. If you have not stored, you can take from here 56 minus 8. But it will be longer task if you have stored. That is good idea. So what is your SNR? First tell me the summation of this F hat square. Okay, it was expected to be huge, and it is 177,680 divided by 716. Divide it with 716. All of you check the summation. One answer is 177,680. 248.156. Let's check. Summation. Check the summation. Summation here it says that 162,304 is the summation. Okay, but whatever it is, like summation, if you will go with this, what you have to do, you have to take f8 square and then you have to sum them up. So here it says that 162 304 will be the summation, and 716, that was your your answer of that error square addition, and the answer is 27227. Now how to, what is the interpretation of this, right? How we will use it? Suppose one method gives me this SNR, another method gives me SNR of 100. Which method is suitable? I will go with this method because here signal ratio is higher, right? Here my error will be lesser. So this is comparative. This is useful for the comparative analysis. That one method gives you this SNR, another method gives you second SNR. Which one is suitable? So that is how you are going to use SNR, right? In the next lecture, we'll start with this compression model, right? And we will go with some Huffman coding. Huffman coding, I think you have studied, but of course you have to consider it in image processing context. You have to consider it. Okay? So tomorrow, next lecture, we will continue with our discussion on this image compression model. Any doubts so far? Okay, so you may leave now. We'll discuss further in the next lecture.
Good afternoon to all of you. This is the last where we stopped in the morning, where we found that for binary input 110.101, we have the decimal value 6.625, using the grammar and semantic rules together using the FTT that we made. Okay. So, binary to decimal conversion, we have seen using two types of grammars. Okay, first grammar was right recursive. This one is left recursive. Okay, so with different grammars and correspondingly different semantic rules, okay, we can achieve the same task. Okay, in both these cases, the attributes we used were synthesized attributes, and we used the bottom-up approach, bottom-up left to right approach, okay, to evaluate our input. Okay, so now we will take one more example. Okay, now say suppose we are given this grammar, right? So this is a very well-known familiar grammar, okay, which we use in variety of examples in compiler design, right? So E E gives E plus T or T gives T into F or F gives number. Now, what can be the semantic rules? Okay, semantic rules are also called informal notations. Okay, so you can give any name to your attribute, right? So what we are doing over here is what semantic rules can be given to this particular grammar so that it behaves like a simple desktop calculator with two functionalities of addition and multiplication. Later on, okay, you can extend this to perform other tasks also. Okay, so basically all our tasks, okay, are addition and multiplication. Okay, if we want division and subtraction, okay, it also can be accommodated using these two operators, right? So that is why this grammar is suitable to develop a simple calculator or simple desktop calculator. Okay, so now let us try to decide that what can be our attributes, right? So for E, T, and F, okay, the non-terminals, we can have an attribute named value, and as we know that the terminals attribute is decided lexically, right? So let us call the attribute lex value. Okay, that is the value which we are going to store in our num terminal, right? So far, I hope all of you are following this, right? Now, what we want to do is we want to uh, design the semantic rules, okay, so that this grammar can be used as a desktop calculator. So now, let's discuss the semantic rules, okay, and let us discuss the SDT, right? So for the first production, E giving E plus T, okay, what we have over here is E dot value equals to E dot value plus T dot value. Now over here, okay, what should be done? Now see, now here you can realize that we have not used any suffix 1 as we have been doing previously, right? So what is the case over here? We wouldn't know that which one is the left value and which one is the right value. So ideally what we should be doing, we should add a suffix of, let's call it E1, okay, on the right side of our production, okay, on our handle, right, so that we can differentiate between left and right. Okay, now for the next production, E given T, okay, the semantic rule says that whatever is the value of T, that will be the value of E. So E dot value equals to T dot value. Now let's have a look at the next production. If we have the production E2 T into F, okay, T asterisk F, not into, okay, this is just a symbol, right? So now if we encounter something like this, then what should be the case of the attribute? T dot value equals to T dot value into F dot value. So again over here, okay, it would have been better if we had used a suffix of 1, okay, on the right side of our production. So we should have written T giving T1 into F. So our semantic rule would be T dot value equals to T1 dot value into F dot value. Next production is T giving F. So over here our semantic rule says T dot value equals to F dot value. And finally F2 number. So what we are doing is F dot value equals to number dot lex value. So far, okay, what we have discussed is that we have talked about the grammar, right, which is very familiar to all of us, right, and we have discussed that if we want to develop a simple calculator, right, then what can be our semantic rules. So when we encounter E plus T, what we want to do is we want to take the addition of the values of E dot value plus T dot value. Whenever we encounter T into F, okay, rather T star F, then what we want to do is we want to take a product of T dot value into F dot value, right? So remaining rules, okay, I'm not going to repeat for those who have just joined the meeting, okay, they are very easy to understand, right? So now um, I am just going to change the slide, okay. Now what we have discussed so far is still visible on your slide. Okay, our SDT, okay, for simple calculator is available. Now, suppose my input is 2 plus 3 into 4, right? So, what should be my answer? How do I calculate it? Okay, so first and foremost, I will need a parse tree, right? And I will parse my input, okay, and using the SBT that we have generated, okay, we will try to compute its answer. Again, what we are going to do is we will use a strategy bottom to up and left to right. Okay. So the values, value and lex value, both of these are synthesized attributes. Okay, lex value is also synthesized attribute decided lexically, right? And value, as you can see, okay, it is obtained by reduction, right? So that is why this grammar is a synthesized attribute grammar. Okay, so now what you are supposed to do is we have already taken actually two examples. Okay, both the grammars were different, right? So we will treat the previous example separately, right? So now in this example, you will do it in your books and then verify it with step by step. Okay, as we discuss on the slide. Okay, so first and foremost, please generate the parse tree in your book. Okay, so if you have not kept your book and pen handy, okay, grab it and generate the parse tree, right? Once you are done with it, okay, after 2 minutes, what we are going to do is we will give input, okay, and then try to compute the or evaluate the attribute. So again, this is with an assumption that you know how to generate a parse tree. Okay, so please do it in your book and then we will compare the answer. So if you are ready with the parse tree, please notify by typing in the chat area, okay, that you have done it. Right. So I know that maximum of you have finished the parse tree, sorry, and we can move further. Okay, Hetul has done it. Okay, what about the remaining students? Okay. It's a very small input that we are trying to take output for. Okay, so it should not take you more than 2 minutes. Okay, to generate parse tree for. And for examples of STD, when you are asked to draw the parse tree, you do not show every interaction with the stack. Okay, you can simply draw the parse tree from the input that is given to you. Okay. Okay. Two students so far. So far only two students are able to generate parse tree for the given input. Okay, then next we are going to verify. Okay, remaining, right? It should not take you really this long. Okay, but if you have not yet understood or practiced the concept, okay, then we'll be generating parse tree for different examples also, right? Because we'll be working upon them to evaluate the attributes, right? So you will get a practice. What we are discussing right now is we are trying to develop a simple calculator using the grammar and the semantic rules that we have defined. Okay, so using the STT, we want to evaluate the input 2 plus 3 into 4, right? Okay, so should I wait for some more time or I should directly move further with the example? Okay, it seems that you are waiting for the answer, so let me just show it to you, right? Okay, so this is the parse tree, okay, for our input 2 plus 3 into 4, right? So if you see over here, okay, we start from E and use the production E plus T, right? And E gives T, T gives F, F gives number, right? And then T gives T into F, T gives F, F gives number, okay, and again F gives number, right? So this is our parse tree that we are going to use, okay, and we will evaluate the attributes for every terminal. We already have the value, right? The lex value is already known, right? And we will try to calculate the terminal non-terminals attributes, okay, that is value of e dot value, t dot value, and f dot value, okay, as and when needed, right? And ultimately what we will have is when we reach the top, that is when we start from bottom and reach the top, that is reach the root, okay, we should have the answer to the expression 2 plus 3 into 4, okay. So e dot value at root, okay, should give me the answer to this particular expression that we are giving as input, okay. So let us try to trace this one, right? So we are going to start by first and foremost, okay, I'm just going to write down the input, okay, num 2, num 3, and num 4, okay, at the leaf nodes of my parse tree, right? Now what we are going to do is we will start to evaluate, right? So first and foremost, okay, our input is 2, right? So our lex value of num is 2, right? Now what happens is num is reduced to f, right? Num is reduced to f, so f dot value equals to num dot lex value. What is num dot x value? It is 2 over here, so f dot value equals to 2. Now next what happens is f is reduced to t, f is reduced to t in the next step, okay. Our evaluation order, okay, determines that which node we are supposed to consider next, right? So f is reduced to t, and so which production are we going to use? We will use the production t to f, okay, and t dot value equals to f dot value. Following this, okay, so t dot value equals to f dot value, which is equals to 2. So far, I hope all of you are getting this. Okay, it is very very simple. Okay, provided you pay attention. Okay, so now what happens is t is reduced to e. T is reduced to E. So which production we will use over here? We will use the second production E to T, and what will be the value of E? What will be the value of the value attribute of E? That is E dot value equals to T dot value, which is equals to 2. So E dot value equals to T dot value, which is equals to 2. So now what we are doing is we are having synthesized attributes, and hence its value comes from the child up to the parent, okay. So that is why first and foremost we were having the lex value of num as true, right? It was used to synthesize f value, it was again in turn used to synthesize t dot value, again it is used to synthesize e dot value, right? So we are starting from the bottom going towards the top, okay, and also we are moving left to right, okay. So we started with the leftmost of our tree, okay, and then we will go about our evaluation. So now next will be plus. So what happens actually over here is now next input, okay, is plus. So when did we decide that next input is supposed to be taken? Okay, whenever we are parsing our parse tree, okay, when do we decide that now we have to take in the next input on our stack, right? When will we decide? Now see, E is not a production, it is not on the right hand side of any of the production. So what we will do over here is we will take the next symbol, that is plus, okay, from our input, okay, and push it onto the stack, right? So now we will consider plus. It is there in our tree, right? But it is e plus is not a production, okay, it is not available in any of the production. So what we will do, okay, we will take in the next symbol. What is our next symbol? It is 3, right? So what we will do is next input is 3, okay, so num dot next value is 3 over here. So now what happens is we have to look for num in any of the production. So where is it available? It is available in the fifth production, and what we have is num is reduced to f. So when num is reduced to f, what we are doing is, what action we are performing, f dot value equals to num dot lex value. So fifth rule we will apply, okay, f dot value becomes 3. Now what happens is f is reduced to t, so t dot value equals to 3, right? Now what next? What is the next step to do? Now we cannot take, okay, any other production, okay, so what we have to do is we have to take in the next symbol. So what is the next symbol over here? Next symbol is multiplication, okay. So far t into, okay, it is not matching with any of the production. So what we will do is we will take in one more input, okay, that is 4, okay, one more value from our input, that is 4, okay. So now next step, okay, what we will have is the lex value for num, okay, it will be equal to 4, okay, that will come from our input, right? So now what we have is num reduces to f. So when num reduces to f, what happens is f dot value equals to num dot lex value. So f dot value becomes 4. Now what is the next step? T into f reduces to t. T into f reduces to t. So what we are supposed to do, what action we are supposed to take? We need to take the action as t dot value equals to t dot value into f dot value. Okay, so like I mentioned previously, okay, so if you do not write the suffix, okay, it may lead to confusion at times, though most of the times it is quite clear, okay, but it is a very good practice, okay, which has not been shown in this example, okay, just to emphasize that giving the suffix is very important, okay, it will um, make our evaluation process simple. So what we are doing is simply we have to take a multiplication of 3 into 4. So t dot value equals to 3 for the 12. So t dot value equals to 12. Okay. Now what we need to do? We have given the entire input is already given to us. Okay. So now looking at the top of the stack, okay, what we have is E plus T. So now E plus T is there in any production? Yes, on the first one, right? So first rule we will apply, E dot value equals to E dot value plus T dot value. So what do we do? Now we add 2 to 12, okay, and E dot value equals to 14, right? So as such, if you look at the input, okay, what output we should obtain when we do 2 plus 3 into 4, we should have answer as 14, okay, which we have found, okay, in the attribute E dot value. Getting this, all of you? Right? So finally, uh, we have used this STT that we have generated, okay, to work like a simple calculator. So any doubts so far? So now moving ahead to the next example, you need to write, okay, now we have taken sufficient examples so that you should be able to write an SDT yourself, right? So I expect the answer from your side, okay, I will give you a time so that you are able to write an SDT. you need to write an STD to convert infix to postfix. Okay. So if the input given is 2 plus 3 into 4, then its postfix should be our output. Okay. So 2, 3, 4 into plus. Okay. This should be my output generated after I provide this particular input. Right. So please take your time. Okay. Wherever you get stuck, please let me know. But try to write an SDT yourself to convert infix to postfix. Okay. SDT means along with your grammar, you must also specify the semantic rules. Okay. Yes, going from left to right, okay, it is yes, sort of compulsory for all STPs. Yes, that's So the thing is that if you so you must write your grammar in such a way, okay, that you are able to do it. See, basically, what it says is that the evaluation must be done, okay, by um, the topological sort on your graph. Okay, so basically, if you have checked your child nodes, okay, if they have been evaluated, okay, no matter what order, still you will be getting the correct answer. But usually we use this particular technique. Okay. See, if you remember, okay, while rest of you are trying to solve or rather get the STT, okay, generate the STT for infix to postfix. Okay, what I want to discuss is in the first example where we counted the number of A's, B's, and C's. Okay, I showed you that there are many evaluation orders which are possible. Okay, but what we usually take is the one that is bottom up, left to right. Okay, but you may get the answers using other evaluation orders also, but what we use is this one. Okay, and hence writing proper grammar with proper semantic rules, okay, that is generating a proper SDT becomes very difficult. So regarding this infix to postfix conversion, okay, a small hint can be given to you that the grammar that we are going to use is the grammar, same grammar you can use that we have written for the previous example where we evaluated any expression. Okay, so same grammar can be used, but you have to decide that what will be the semantic rules. Okay, what action you will perform when a particular production, okay, for a particular production what will be the action, okay, that you have to decide. Okay, so for the SDT to convert from infix to postfix, okay, the grammar will remain the same. Okay, you can use this as a hint. Yes, so far yes, only addition and multiplication. Yes, yes. So I'm just trying to work upon this particular input. Okay, depending on different inputs, okay, your first tree generated will be slightly different, and then your SDT also, the rules that you define, okay, they will be different. Yes. So only for this particular input, okay, we are talking about. Then later on, you can have a different input, okay, and for it you can write a different grammar or yeah. So shall we discuss the answer? Right. I hope that all of you are getting an idea of what you are supposed to do. Okay. Because first, what you are supposed to do, if it is clear to you, right, only then you can go about what you are going to do. Right. So now here you can see that the grammar is the same. Okay. But a very simple semantic rule, okay, has been um, written to form the SDT to convert infix to postfix. Okay, so as our grammar is the same, input is the same, so path tree will be the same, right? The action that we are going to perform, okay, let us try to understand it. What we want to do is whenever a number is encountered, what we will do is we will print the lex value of the number. Okay, here I have written L value for short. Okay, basically what I want to do is I want to print the um, lex value. If T into F we encounter, okay, then what I want to do is if that production is encountered, then we will have the value multiplication printed. If it is T plus sorry, E plus T, okay, then we will print plus. So for our input 2 plus 3 into 4, our postfix should be 2 3 4 into plus. So let us check that with these semantic rules are we getting the postfix from the given infix or not. Okay, now what we are going to do. Yes, it looks exactly like that, right? Because what we are doing in our postfix output, okay, we will parse through the parse tree in the way as you have mentioned, okay. So yes, it looks very much like it. That is true, right? And as such, the grammar and the semantic rules are very simple, okay. So though you may find that how to write STD to convert infix to postfix, but the solution is very simple. Okay, so let's take the trace, right? If there is anything else that is to be mentioned, okay, please let me know. Okay, otherwise we are just going to uh, Yes, there can be other mechanisms also. Okay, as I have discussed in the previous example. Okay, you can have other solution. What you are supposed to do is you have to take a trace, right, and check whether you are getting the output which is desired, right. If the desired output is obtained, then it is perfectly fine. Okay. So in all these examples, it is very much possible that you may have some other solution, but you have to check it thoroughly, right, for the input, right. Okay. So now what I'm going to do over here is I'm going to name uh, these semantic rules with the numbers 1, 2, 3, 4, and 5. Okay. Now what I want to do is I want to show you with this example, as you have with an assumption that you have understood all the previous examples properly. Okay. What I'm going to show you with this example is that you can use the same FDT. Okay. If you want to go top to bottom parsing, if you do, or you do bottom up, okay, you will end up with the same answer, right. So what we are doing over here is I'm going to add some nodes into my parse tree, okay, so that it will facilitate me to go top to bottom. Okay. So what I'm doing over here is first and foremost I have given numbers to these semantic rules. Okay. So the actions that are to be performed, okay, that I'm going to add into the parse tree as nodes. Okay. So let's see how I'm going to do it. So now, how these nodes are added, please try to understand. Okay, let us consider that our production says something like this: E gives E plus T, and whatever is our action, it is part of my production. Let us consider it something like this, right? Then our tree, what we will have is, if we start from E, that is our root. Okay, then we will have E plus T, and then the action, it is also as another child of my root node. Okay, so I have added one over there, right. I hope you are following this notation, right. So once again I am repeating that in this example, if I want to take top down approach, okay, then what I need to do, that I will add the semantic rules, that is I will add the action I need to do for a particular production, okay, as part of production. Okay. So now say suppose we are having E gives T, okay, then we will consider two childs of rather two children of E, okay, T and 2. Same goes for T gives us F, okay. So what we will do is T gives F and T gives 4. Okay, and likewise. So this is how I have made changes in the tree by adding the action to the production. So I'm just showing you the previous slide wherein, okay, this was our parse tree. Now what I'm doing is, if I add the productions, okay, with the action, then the tree looks something like this. Now we will take a trace from top to bottom, and whenever the action is encountered, the action will be performed. So actually what we are doing is we are doing the same task, okay, but we are now doing it with a top down approach. So if we are changing the approach, naturally we will have to make some changes. Okay, so these are some changes that we have done. The grammar remains the same, the action remains the same, only the representation is changing. Okay, so now if this tree is acceptable to everyone, then what we are going further is, now we are going to take a trace from top to bottom. Okay, top down approach is being taken. Okay, so now first and foremost, the numbers that we want to work with, okay, we are now giving the lex value to the numbers, okay, 2, 3 and 4, okay, that we are writing so that it becomes easy for us, right. So now once our parse tree is ready, okay, for tracing, let's move further. So now what we are doing is, we are starting from the root. We are starting from the root. We will take E, then the left child of it, again E, again left child of it, T, again left child of it, F, and again left child of it, that is num2. So now our output is generated because of the fifth action, okay, node number 5, okay, that has been represented in the part 3, okay, that is now being considered, okay, and it is printing the a lexical value of num, which is 2. So now in the output we are having 2 being generated because of the printf action, right? Now which is the next node I should take? We are taking a top down approach, but we are moving top down left to right, okay. So what we will do, next node we will consider is 4, okay. So now what we are supposed to do as an action, okay, when 4 is encountered, there is no action associated, right? It is empty, empty brackets, right? So what we do nothing, right? So in this step we are not supposed to do anything, right? And we will take in the next node in our parsing. So next node that we will consider is node 2, right? So now this is the next node we are taking, right? What action we are supposed to perform? See, whenever the numbered node is traced, okay, what we are supposed to do, whatever is the action that we will perform, right? So what action we have to take? Again over here, nothing to do, right? So we will move ahead. Now, next we will consider plus, then there is nothing associated with it, okay, so we will take the next, that is T, then again T, then again F, then number 3, right? That node we will take, right? So what happens when that node is taken into consideration, okay, we will have a lex value given to num as 3. Now next node, okay, that we will take is 5, okay. So what is the action we are supposed to perform? The action we are supposed to perform is we need to print the lex value of number, right? So lex value of num, so that we have printed in the output. So in the output you can see previously 2 was printed, now another value 3 is also printed, right? Moving further, what we do is next node that we will consider is 4, right? So what we are doing over here, nothing to do, there is no action associated, it is empty bracket, right? So we will move further. So now what we will do, we will consider multiplication f and num. So now lex value of num becomes 4, right? And then what we will have is the action we will perform at node number 5 is we will print the lex value of num, which is 4. So now in the output you can see, right, that our output is now having one more value, that is 4, okay. Now we have to move further, okay. So far, okay, it is very easy because as such a lot of actions have not been performed. We are simply performing the action number 5, right? Because action number 2 and 4 are not having any action associated, right? It is just empty bracket, okay, nothing to exit. Now next node that we will consider is 3. So now what we are supposed to do over there, right? What is the action associated with 3? 3 is we are supposed to print asterisk sign, right? So we are printing the multiplication sign in our output, right? So now our output is 2, 3, 4 into, right? Moving further, next node is 1. So what we are doing is our action associated is we have to print plus, so that we have printed, right? And then what we are doing is we are reaching the root. Okay, so our entire tree has been parsed from top to bottom. Okay, and our output, that is the postfix for the given infix notation, is given to us. Okay, so here we are taking the top down approach, and in this case what we are supposed to do is we have to add the action. So basically whenever we are having synthesized attributes, okay, uh, so over here our attribute in this case, okay, it is some action. We are not having any attribute that we are evaluating, okay. So in this case some action is to be performed, okay. So there may be some action associated with a production, or there may not be an action associated. Okay. Similarly, you can understand that if some attribute is having any value, if it is to be evaluated, then there may be an attribute associated with a production, okay, or it may not be the case. Okay, so this is an example just for you to understand that if we are taking another approach, okay, its behavior will be similar as you can relate, okay, and you can also get the same answer, okay, using the top down approach, right? So now I have also added the example, same example with the bottom up traditional approach, okay. So now let us see that very quickly and then try to compare, okay, what is the difference between top down and bottom up for this particular example. Are we getting the same answer or not using the same SDT? Okay. So now I'm going to demonstrate the bottom up approach, okay, for the same SDT that I have written to convert infix to postfix. Okay. So when we are starting from bottom, what we are supposed to do? We have to take the leftmost child of our parse tree, right? So what we will do is we will give the input. Okay. The lex value of num is 2, right? So now num is reduced to f. We are taking bottom up approach, right? So num is reduced to f. So what we are supposed to do? We need to print the L value of number. So now my output is showing 2, right? Initially, okay, it was there was no output generated, right? So now what we have is our output is 2. Now f is reduced to t, right? So now what we are supposed to do? When f is reduced to t, we are not taking any action because action is empty, right? Now next we will take t reduces to e. So in this case again there is no action to be performed. Okay, as you can see over here, right? That there is no action. It is empty bracket, right? Now what we will do next? Plus will be pushed onto the stack, right? And we will take into account the uh, next node, that is num. So now what happens is we are taking in the next input, okay, from our input value 3. So 3 is put onto the stack, right? And what we are doing it is reduced to num. Okay, so now num gets a lex value of 3, right? Next what we are doing is num is reduced to f. So what happens is we are supposed to print the num value of we are supposed to print the lex value of num. So 3 is being printed. F is reduced to t in next step. Okay, so no action to be performed as you can see over here. Okay, in the semantic rules I have highlighted that we are not supposed to do any task because with the production t to f there is no action associated. Next what happens is next we will take multiplication, it will be added onto the stack, and now next number, okay, 4, okay, that will be taken, and what we are doing is we are able to reduce 4 to number, okay, so now num will have a lex value of 4. Next what we do is num is reduced to f, so what we will do is we will print 4, right? Till this point, okay, you must understand that rest of the symbols are still on the stack. Okay, so those will be evaluated. Okay, whenever they will be evaluated, at that time they will be popped up. Okay, so far whatever we have been doing is just pushing, and only 3 values have been popped out. Okay, now what is the next step to do? T into F reduces to T. So do we have a suitable production? Yes, we have. And what we are supposed to do? What is the action we are supposed to take? We need to print a multiplication sign. We need to print asterisk. So that is what we are doing, right? So when T into F reduces to T, what we do is we print asterisk sign. So you can see it on the output. Okay, 2, 3, 4, and multiplication sign. Next step, what we are doing is next step is E plus T reduces to E. What we do is we print plus. We have printed it. We have reached the root. Okay, we have gone by the bottom up approach, right? And we have generated the output. Okay, which is the postfix for the given index, right? So we have taken this example both the ways, okay. Mostly you will be going by the bottom up approach, okay, but if at all you want to go by some other approach also, okay, then also you will get the correct answer. But this is what you are supposed to do: take bottom up, left to right approach, okay, and evaluate your input. So any doubts so far for the examples that we have discussed? If you find some other solution, okay, if you find some other grammar, if you find some other semantic rules, okay, that will parse your input and generate proper output, okay, that also can be counted as valid. So what I would suggest is, if you want to try it out, then you may, okay, and then next time when we discuss in next week, okay, when we have a class, then what we can do is, at that time we can check for other solutions, okay, so you may send them to me, okay, we can verify it, and then if those are correct, okay, that also can be a solution, that also can be an SDD for a given age. Okay, so now let's take a next example, okay. So far whatever examples we are taking, okay, they are all s attributed grammars, okay. We have not yet taken any example of inherited attribute, we have not taken, okay. So that we will take in next class. Now one more example, okay. Let's take now, okay, I want you to write an SDT to build a syntax tree for this particular thing. So what you are supposed to do, first and foremost, I'm sure all of you know what a syntax tree is, right? So for this input, what will be the syntax tree? It will look something like this, right? So what we are having is, we are having in total 5 nodes, okay, and each node has got a left and right pointer. For the leaf nodes, the pointers are null naturally, right? And for multiplication and addition, the node containing the value asterisk and plus, okay, the left and right child nodes are pointing likewise. Okay, so this is how our syntax tree is built. Okay, this is what we want to generate, okay, using SDT. So now for this particular input, okay, this is the syntax tree. Now you have to write an SDT to build a syntax tree. Okay. So we have 5 minutes before I'm going to conclude the lecture. Okay. So its solution we will not discuss. Okay. Right now, I want you to try this. Okay. And then we will discuss this in the next class. So you can start doing it right now, or if you want, you may take a break also. Okay. But if you get stuck anywhere, okay, I'm still available for next 5 minutes. Okay, so we can discuss if you have any doubts. Okay. Uh, for num, we have an action push num to stack. Okay. For the operators, what we will do is for each operator we will make a new node. Okay, and then add first pop to the right, second pop to the left, and put this node on the stack. And at the end, pop the node from the stack, which will be the root of the syntax tree. Okay, yes, this can be a possible approach. But here you are forgetting one thing, that when we are trying to build our syntax tree, we are having 5 nodes total to make. Okay, so 2, 3, and 4. Okay, they are also nodes of your syntax tree. Okay, not just plus and multiplication. So in this SDT that you are required to build, okay, I want you to build for each symbol. Yes, so you have to make a node. Okay, for that also. Yes, they will be nodes as you have written. That is correct. Okay, so you need to write the action to make those nodes as well. Okay. Yeah, that is absolutely correct. Okay, it must be a node to be connected to another node, right? So what you are supposed to do is you must write an SDT such that, okay, with every symbol, okay, it creates a new node, and what it does is it connects, okay, on the left or right side depending on the logic that you decide. Okay. So like I said, there are multiple solutions possible, and if it gives you the correct answer, it will be considered as valid. Okay. So in the next class, I will give you the solution, okay, which I found easy to build the syntax tree. Other logic also we can try out, okay. And so for now, I am concluding the class, okay. Right, so I am stopping the presentation, right. And make sure that you write the SDT, okay, before you come to the next class. Okay.
Good afternoon, students. It's Thursday and 2:30 p.m. and a BDA lecture. I'm not certain how come the lecture was there before 2:30. Maybe are you on schedule? I mean, are you suppose expecting my lecture right now, right? As per Thursday schedule. Students, I believe I have connected to right classroom. That's 7th semester. I know few of you at least by faces or names. And you're expecting BDA lecture right now, right? It's Thursday, 2:30 p.m. Yep. Uh, so most of you, I mean, most likely you would have received email also for the schedule starting Saturday onward for 5 days in a row, right? You would have received that email also. Have you received email from CKB sir for schedule Saturday onward, this Saturday onward? Okay, all right. So Fine, let's get started. Actually, big data and analytics. Okay. So we have one lab on Saturday, this Saturday, 3:30 to 5:30, as per the schedule, and that will be the last lab for the semester, right? Somehow the connectivity is little off today. I mean, so give me a moment. Meet. So by the time know that previous year sessional papers have been shared with you already. Uh, at the time there were like 3 or 4 or 5 sessionals, right? So you may refer them for your upcoming exams. Okay. Uh, and if you may have any questions regarding any topic discussed or questioned in that sessional paper, you can email us. Okay. So today we are just continuing the distributed systems few topics, and then we'll move on to an algorithm, a research paper actually. Okay. Uh, so if you remember last previous lecture, we were talking about the global state and the logical time clock by uh, Lampert, right? So there is actually a limitation of that logical clock. I repeat, there is a limitation of Lampert's logical clock. Uh, you may Google it, or is already provided in the PDF file. The instructor's material is provided. But have you thought? I mean, if anybody got chance to read or think, there is a limitation. Can someone think what is it, or at least can you refresh the knowledge or information of previous class? What did we do? What we talked about logical clock. If you remember, it was all about events, right? So every single event is considered to be a milestone, like an it will be attached with a number, and that number is monotonically increasing, and that's what it is. I mean, that's what the logical time is. Okay. So as per that, there were processes also involved, right? Process A, process B, or PI, PJ. And if you try to remember that PDF file where it was talking about uh, two separate processes also. Now, what can be the limitation? I mean, if you remember, it was saying that there are sequence numbers kind of uh, monotonically increasing. So, and I was telling you that there will be logical clock associated with separate events. Okay. So, what can be the limitation? I mean, how do you see this multi-process and the logical time? So Nidhi says not able to synchronize time across entities. fine. So something on those lines, yeah, correct, I would say. So here you need not to at least so yeah, something on those lines. Basically on multiple entities, uh, which is nothing but processes, right? So their own events. Let's say process A has event at certain point, and process B has event at certain point. Can you correlate these two events? I mean, that mathematical formula, if you remember, happened before relationship, like A arrow B indicates that event A happened before event B. Now, provided event A belongs to process A and event B belongs to process B, can you really justify this logical time? And the answer is no. Okay, because they have their own local or individual generator, clock time generator, right? And hence they both would have their own so-called number or logical time, and hence across the events you actually cannot say that A arrow B across two separate events is not theoretically correct, is not theoretically correct at all. Okay, so that's the limitation of logical time clock provided by Lamport, and hence other clocks like vector clock and other algorithms were described, which we are not gonna refer for now because they are gonna be a little more complex. And unfortunately, why am I not describing that? Because I don't have any of the implementation information available. So what I'm talking is like it will be theoretical, and I won't be able to justify, or I'm myself not convinced with whatever we might be just describing there. That's because it's more like a theoretical information, and I personally unless I have some kind of practical or hands-on base of certain information, it literally, I mean, it for me it is kind of incomplete. uh, Hence I would not go in depth of the remaining possibilities of logical time clock. Okay, but know that there is little base, something called vector clocks and more. For us, it's not in our syllabus, so if you may want, you may explore, but know that logical time clock by Lamport is the only one which we are describing. Okay, we are not describing any more further concerns in that. Okay, so you may open that PDF file which is already shared in maybe lecture 16 or so, which is 17 or so, which is actually about let me open that from my mobile at least. See, still not getting. I mean, I'm trying to connect my laptop, but it's still not getting. So hopefully these 7 days we would be able to connect smoothly, and hopefully my laptop and the network doesn't give a lot trouble, because the weather is also getting little humidity, like hot, and then devices, back to back use of devices are kind of troublesome too. So we have talked about Lampert's logical clock happened before relation, right? And so we have not gone in the implementation details. I think we just started last time talking about the implementation detail, and then I had to switch off the lecture. So guys, confirm that you are able to see my screen. is nothing but a mobile phone screen only. I'm connected to Google Classroom, and you also have this PDF file in your one of the lecture, maybe 17th or 18th. Okay, just confirm that you are able to see the screen for now. I'm switching because I want to see the chat also, but then are we connected? Hello. Thank you. Uh, Fine. So actually, last lecture we stopped here, where we were talking the implementation rules for Lampert's logical clock, and let's just describe for a while. But then we also started talking about the limitation, which also is following. Okay, so clock Ci is incremented between any two successive events in process Pi, right? And usually D has the value 1, so it's very much like a counter only. Okay, for a certain event Ci, I'm sorry, for a certain process Pi, the clock Ci gives value to event I, okay, which will be nothing but Ci plus 1. Okay, hopefully, and if A is the event of sending a message M in the process Pi, then message M is assigned a timestamp Tm. On receiving the same message M by process Pj, Cj is set by following rule. And this is about the communication. Okay, so logical time clock is different, and the communication via message passing is different. And this rule 2 is actually talking about updating the counter value. So sometime it will be updated by 1, and some other time it will be updated based on the maximum formula, which is the existing, as well as whatever the timestamp you have received from the message plus the D is again plus 1. So this maximum has its purpose here, and that mostly is about which one is the latest event, to identify older or the current information, like current time clock. Okay, so for the jth, Cj is set by following rule, which is Cj is equal to max of Cj, whatever is the current value of Cj, out of that, or whatever you have received from the message, which is Tm, timestamp, which was actually belonging to ith process. Okay, so that CIA, you see Tm is nothing but CIA, that is the logical time clock of process I, right? So there are two processes here, Pi and Pj, and the time clock of process J will be updated based on the time clock of process I. In which scenario? Because this is the sending of message scenario. Okay, that's when two processes are involved, and that's when either the either your own time clock, which is greater, or the other person's time clock plus 1, whichever is greater, that will be the next uh, time clock for uh, jth logical clock. See, it's nothing but it's actually just it has to make sure that it is maximum of highest. I mean maximum of two information. Is basically it's conforming to the property of monotonically increasing value. So when there are two processes involved, and what should be the next logical time clock, then the answer is both of their whichever is higher, and maybe plus 1 part. I mean Cj is already incremented in a way, so Cj or whatever is given by the other process plus the D is like the factor. Okay, which is usually 1, but whatever is for the system it is. Okay, so we have seen this use of max in another algorithm, there where the use of max was to find out the current message or the previous message, right? Here the use of max is very much like to get the latest monotonical information. Highest of 2, I mean that's what will be the new highest. Okay, likewise that highest of 2 will be the new highest, something like that. Okay, uh, so fine, this is all talking about the total orders. Let me tell you the limitation part. Yeah, so limitation of Lampert's logical clock. So let's try to understand this. Okay, if A arrow B, then we understand it is the logical time clock A is less than logical time clock B, right? That also means event A has happened before event B, right? However, the reverse is not necessarily true. I mean, events A and B may or may not be causally related. Now, this causally word, if you understand, they may not be dependent. Causally, I mean, maybe like they may not be dependent. For example, in the message passing, if event A is message sent and B is message received, they are called causally related. But in other scenario, uh, imagine A is a message sending of process A in some communication 1, and imagine that B is maybe message receive or message sent, doesn't matter what it is, but it is of communication 2, like there are two separate communications happening, and this event A and B belongs to two separate communications. In that regard, A and B may not are not causally related. Okay, let me repeat this. If for the same communication, A is message sent and B is message received, we say that they are causally related. Now imagine the other way around, where there are two separate communications happening and A and B are part of those two separate communications. In that case, they are not having any dependencies or relevance. They are not causally related, right? In that case, what will happen? The diagram what you are seeing, right? There is in process 1 there is event E1 E1 2. That way in process 2 there is event P2 E21 E22, okay, etc. Right? What is they are trying to say is the reverse may not be true. That is what they are trying to prove, and the reason behind it is causally related. They may not be causally related. Okay, so we can see that logical time clock E11 is less than logical time clock E22. Yes or no? Right? And the logical time clock E11 is less than logical time clock E32. That is the third event actually they are moving on to. But then E11 arrow E22, that means E11 happened before E22, that is holding correct, but E11 happened before E32 is not true. Can someone say why, or can you understand why from the diagram? See, E11 happened before E22, that you are confirming. The reason being there is an arrow from E12 to E22. See, there is a line, slanting line between P1 and P2, right? In the diagram, there is a slanting line between P1 and P2. That actually indicates the cause effect. I mean, big cause and causal effect. It actually indicates cause. That's when you are able to say that E11 happens before E22, because there is a connection. I mean, there is a cause. Okay, but then there is no cause between P2 and P3, or there is no cause between P2 or P3. That's why I cannot say E11 happened before E32. I hope that makes some sense, right? There is no cause. I mean, the events are not related or causally related. Uh, so what will happen? So the idea here is you cannot just connect two times in all the scenarios. You will be only able to connect times if they are causally related. That's the bottom line. You can only connect times if they are causally related. Otherwise, you cannot connect time. And we know that in systems there may be multiple communications or multiple messages being passed. There will be multiple processes. So there may not be all of them may not be always causally related. Uh, I hope that makes some sense. This is the limitation of Lampert's logical clock, which is nothing but because of possibility of because of possibility of not having any causal relation. Uh, Even though you may think like one A happened before B, uh, you can prove. I mean, the clock time wise, it will look correct, but really in actual, it may not be correct. That is what they are trying to uh, confirm here. So it's more detailed there, but at least the diagram, that slanting line from E1 to E22, that's the primary point here. That is actually indicating the causal relationship. Uh, that's when you can still say E11 arrow E22, but otherwise anything else E11 arrow E32 you cannot say that, even though E22 and E32 are same timeline. If you see, both the dots are following on the same vertical uh, space, right? Because space time, they are following on the same timeline. You still cannot say E12 E11 is less than E32. uh, Guys, do you understand? Because it is a space time diagram, on the time side E22 as well as E32, the value looks similar, right? On the timeline. Yes or no? E22 and E32, the value is exactly similar on the timeline, right? Global timeline. They here you see it is like X versus Y. So X is space and Y is global time. So if we consider global time, which is the sorry, okay, okay, my bad. X is actually global time axis and Y is the space axis. So if on the x-axis, which is global time, if you see E22 and E32 are holding the same value with respect to global time, but though they hold the same value, they you cannot replace expressions. I mean, you cannot replace those arrow relations. You can say even one is less is even one happened before E22. You can say like that, but you cannot say that even one happened before E32. You cannot say that, and the reason being they are not causally related. So that's the limitation of Lampert's logical clock, which is though you might have same logical clock time for two separate events, but you may not be able to relate the exactly same way. You may not be able to relate exactly same way. Fine. So I think this is more than enough, and then see there are more like vector clocks and all. I will not go in depth of that. The only reason is I don't have any implementation available for this. I myself have not gone into the implementation part, uh, and hence it doesn't interest me a lot, honestly. Yes, but for understanding sake, for starting the fundamental sake, it definitely is needed, and that's why we have described it. Okay, fine. So with that, we'll move on to the last topic. Hopefully I haven't uploaded here. Okay, I'll take a break for a few minutes. Let me switch network. Okay. Guys, I'll take a break for a few minutes. Yeah, sorry about that. Yeah, I just. So, see, the thing is, this particular process is hanging. I was trying to email myself something to myself, and then present, but that, I mean, maybe a deadlock there. What is on plate is another research paper called a priori versions based on map reduce for mining frequent patterns in big data. That's most likely for the next lecture or remaining type of time of current lecture, but that's on plate. And this particular process I'll have to force kill it. It's kind of hanging. I'm holding some resource which because of which my system is not able to move. Okay. uh, but then I should have uploaded this prior to now, which I'm sorry didn't happen. So give me a moment. I'll come back. Okay. I'm sorry about this. So by the time I can definitely describe this. Uh, in the past, we talked about a priori algorithm. How many of you got chance to read it or look into it? The algorithm name is a priori. Anyways, so we'll look into it further, uh, whenever the time is right. So let's continue with. So you may please pin another window and confirm that you are able to see the PDF file of distributed shared memory. One of you please confirm that you are able to see distributed resource management, distributed shared memory file. Thank you. So we'll move on. So this is the last topic in this with respect to distributed computing. Okay, this is the last topic, and it is again very much theoretical and very brief only, like maybe 5-10 minutes. Just because it's there, I thought I should touch up. Again, I don't have any implementation coding or demo available in this regard, and that's when I'm not touching a lot. Okay, let's just see it. So the inherent limitation of distributed computing or distributed systems uh, is having absence of global clock and absence of shared memory. So what is the solution about not having global clock? The solution was just to start, the solution was Lampert's logical clock. And we also learned there was a limitation of Lampert's logical clock. We just understood one simple limitation by that diagram, which was mentioning that even though the two time clock, logical time clock will look same, but you cannot really utilize them if they are not causally related. I believe that diagram made some sense to you upon that particular topic. So we are moving on to the solution for shared memory, like solution for not having shared memory. So as we described, or as I give you a simple analogy, that imagine there are 10 friends and there is no WhatsApp group. Will you all be able to stay on the same page? I mean, will you all be able to have the latest up-to-date information at a time about all 10 of you? Then the answer is no, right? If there is a let's say WhatsApp group of 10 friends, and then whatever information is dumped there, at least there is a chance that all of you are on the same page. Again, you may feel like if somebody has not read, uh, he may not be on the same page, but that's a different story. I mean, this is just an analogy, not a complete correct scenario. So I hope that makes some sense. The WhatsApp group of 10 friends, that scenario makes some sense to you, right? So there's no shared memory as we understand. So then there is a topic called distributed shared memory. Okay, now how it works. So the short form for this one is DSM. What is it? The distributed shared memory, it implements the shared memory model in distributed system. So it's actually a model, it is not physical. Okay, it's not physical because people used to have network file system and used to have SAN like devices. They were used for shared memory criteria. So that was actually hardware solution of having a distributed memory, okay, shared memory. But this one, what exactly the DSM actually, it talks about a model. I mean, a software or a logical part, not the physical hardware part. No, it's not talking the physical hardware part. No. So DSM, it implements the shared memory model in distributed systems which have no physical shared memory. Yeah, that's what it is clarifying. It has not got physical shared memory. Okay, no. This is just a on top of physical shared memory, some kind of algorithms and data structures which will model it as a distributed shared memory. Fine. So the shared memory model provides a virtual address space. So this is the logic behind it. It provides a virtual address space shared between all nodes. To overcome high cost of communication in distributed system, DSM systems move data to the location of access. I mean, this is uh, about locality of reference. The locality of reference is a common term. We have talked about locality of reference in the past. There where we understood moving data to code and moving code to data, right? So at least DSM originally, uh, was thought to have, move data to the location of access. But then currently, because of the big data scenario, it is also the other way around where you don't move the data, but you move code. So this third line, actually third bullet, is little different in current scenario. Okay, but both of them actually has to do with the locality of reference kind of you know concept, locality of reference. Anyways, data moves between main memory and secondary memory within the node and between main memories across the nodes. Okay, so you know that all the nodes will have secondary memory, which is nothing but, let's say, hard disk, and main memory, which is RAM, right? So data will move from main memory to secondary memory. And what is it called? Can someone tell me what is it called? If data is moving between main memory to secondary memory, what is it called? And that is actually happening in a regular OS also, and it is called uh, any idea? If all the data you cannot fit into main memory, or you may want to have more data into main memory, logically you guys do something behind the scene in operating system, which is called Yeah, yep, right. We were virtual memory. Yes, it is actually when data moves from main memory to secondary memory. Uh, pages, paging. I believe you understood that page fault and page will be loaded. So paging and virtual memory. Yes, it is virtual memory, right? And then this is taking it further. So data will move from one primary memory to the other primary memory across nodes. Okay, so that's how distributed shared memory is basically achieved. Each data object is owned by a node. Initial owner is the node that created the object, and here the object means data. Okay, so that's whoever creates the data, that node is the initial owner, but then it will move from one node to other node, and ownership can change as object moves from node to node. When a process accesses data in the shared address space, so see that there is something called shared address space, which is very much like your virtual memory concept. Okay, but here this shared address space is across multiple computers. The mapping manager, this guy is the software part. The mapping manager maps shared memory address to physical memory. So there will be two address line. One is the shared memory address line, and there will be actually physical memory address line, right? And there is something called mapping manager. That's the software piece, like service piece, which will actually so for whenever you will access certain memory at, let's say, address 2000 in the shared memory address space, which is, let's say, DSM, the mapping manager will actually find out where that 2000 address is, from which physical memory the 2000 is mapped. So let's say 2000 is actually mapped onto node 5, 5000 primary memory location. That is, under the hood, the mapping manager takes care of those things. So uh, I repeat, 2000 shared memory address may be mapped to the 5000 physical memory address of your own computer or maybe some remote computer, but those information and those architecture is taken care by the mapping manager. So yeah, this diagram may make some sense to you. Actually, it should be upside down. I mean, just to understand, but doesn't matter the direction. So you understand that node 1, node 2, node 3, all of them has their own primary memory, right? Part of the primary memory would be occupied by or utilized for distributed shared memory. For example, like this diagrams, like the gray part of the memory area. Let's say they are occupied or utilized for DSM, distributed shared memory. How mapping manager knows that those address spaces, physical address spaces of individual nodes, right? And then mapping managers, it actually multiple pieces of software, but it is done logically, single person mapping manager, which actually provides something like this on the bottom, which is your shared memory. So let's say this is here, 1 GB, this is 1 GB, and this is 1 GB, for example. Then the shared memory totally available is approximately 3 GB, right? And how will it work? I mean, it's very much like a software piece. There will be mapping, and we understand what mapping mean, right? So that's about it. I mean, there are advantages of distributed shared memory, right? And as we understand, of course, there will be advantage if we have distributed shared memory, uh, and there are algorithms also. I'm not going in depth of this. About DSM, you should just know this basic concept, how it is achieved. Algorithms are still theoretical only, and that's when I don't want to go and talk about those algorithms. See, they are all primarily looks like just very theoretical concept. I don't see any implementation or architecture designed here. That's when I'm not taking up any of this. Okay, but then at least the last slide, it talks about a case study named Clouds. It was developed at Georgia Institute of Technology. The virtual address space of all objects is viewed as global distributed shared memory, right? The objects are composed of segments, paging and segmentation. So they might have chosen the name segments here, which are mapped into virtual memory by the kernel using the memory management hardware. So they might have some extra hardware also. Okay, a segment is a multiple of physical page size, and this is again we know, right? Segment and page we know, right? So for remote object invocation, the DSM mechanism transfers the required segments to the requesting host. So at that time when this was designed by so and so institute, right? It was actually the data transfer was happening. Okay, the remote object invocation DSM mechanism transfers the required segments to the required host for the locality of reference. But know that this is still transferring the data, not the code. We are not talking about transferring code. Okay, and on a segment fold, we understand what is fold, right? Page fold, very much like that segment fold. The location system object is consulted to locate the object. So this location system object is very much like your mapping manager kind of thing. The location system object broadcasts a query for each locate operation. Uh, why the name location? Because it locates. Okay. The actual data transfer is done by the distributed shared memory controller, DSMC. Now, as we are talking about shared memory here, memory can hold variables also, and memory can hold your function code also, right? So when we actually talk just the memory, and memory can hold both the things like variables as well as the function code, right? Not the code, but function binary code, right? So understand the concepts are applied for both the things, irrespective of whether they are variables or they are the function binary code. For the memory, they are just data. They are just information. So when they are saying they may transfer information, right? Transfer the required segments, or even in the previous slide when they mainly talked about transferring, they are supporting the architecture. It doesn't really matter whether it is the data or is it a code. So that part is not is above the layers. This is like down the line, I mean underlined. Okay, so we just talked about this one case study about distributed shared memory. Why I took up, because when it was developed, somebody at that time, I don't have the year when this was talked or developed, but at that time somebody named it clouds. And we understand right now, the virtual address space, like we understand cloud, right? We understand Google Cloud and Amazon Cloud and all, and we use it, right? But know that that might have originated, you never know where. It might be coincidence to see this name cloud, but then that what happened years ago, uh, when somebody tried to develop distributed shared memory. So can you see distributed shared memory? The roots are lying actually the clouds. What we use nowadays. Their roots are actually. Can we say this distributed shared memory cloud? Google Cloud or whatever. The cloud is implementation of distributed shared memory. At least just to start with storage purpose. Processing is next thing. Okay, processing is next thing. But if you are just thinking of storage, can we say that distributed shared memory is actually uh, uh, the real implementation is what we see the cloud? I repeat, can we say that the cloud is the implementation of the concept distributed shared memory for storage purpose at least, right? Uh, right. So it was a coincidence, or that's the beginning, this particular name. Okay, but DSM, why just I touch this topic, it's a small topic, distributed shared memory, but you understand that this all things are behind the scene. So with respect to distributed systems, what we have talked introduction, we have talked about uh, logical clock, we have talked about global state, then we have talked about distributed mutual exclusion, and you also understood that there will be deadlock. So there are actually algorithms of there are algorithms of process scheduling also that we have not described, but there is something called this distributed shared memory we have described a bit, right? So these all things are there, which are actually roots for our cloud and big data and analytics, etc. So with that, distributed systems, I think I should put a hold on to it. You may explore more on your own interest. Okay. Uh, Yeah, that's about it. That's about distributed systems. We are not going to talk any more things with respect to distributed systems. Okay. So now, yeah. So let's continue with our big data and analytics algorithms and a few different more things. Okay. So we have around how many? 5 lectures yet. Oh, really? Am I counting it right? Tomorrow and the no 3 lectures. Tomorrow Friday lecture and 2 more of next week, which will be however they are scheduled. Okay. So we have 3 more lectures, and I'm planning to bring you. Uh, uh, let's see. I actually wanted to communicate to one of my friend to deliver you some talk. Okay. But then I would have to check on the schedule because yesterday late night we got updated timetable, right? At least timetable for next days. So, but then let me just tell you, you may go to YouTube and maybe you subscribe to channel called Core Basics. If I'm not wrong, that's the channel name, Core Basics. Okay, and let me just type it for you. Core Basics by Dhaval Patel. Okay, that's one of us. Can you guys try googling that Core Basics YouTube channel? Let me write it. I typed it, but I typed it in another window. Let me just type it in here. Core Basics by Dhaval Patel YouTube channel. Okay. So guys, confirm that we are connected and you guys are able to read the chat in our window. Core, yes, Jainik. So all of you, please, Google this and subscribe to. See if you want to subscribe. I mean, I'm not, you know, advertising my friend's channel. No, okay. He's one of us. I mean, he's from DDIT only. To give you history, in the year 1997, myself and his, I mean, photograph were there in the newspaper in the Kheda Avrutti of Gujarat Samachar or Naya Padkar because we were in 10th standard. The result was out. Okay, and both of us scored, good in respective area, local to Kheda district, hopefully. And then we both, at that time we didn't know each other, but then we joined 11th Science in RPTP school in Vivi Nagar, 97 to 99. We were in the same class um, for 11th and 12th. And then our results, of course, 12th results were out too. And I scored a single 1 marks grade more than him, but honestly I know he is actually a genius and I am just a sincere and hardworking guy. Okay, so on the day when we were going to for admission, I actually scored 1 more marks, and maybe in practical also I scored few more than him. I'm not aware of practical. I don't remember that for now. But at Ahmedabad at LD Engineering College, we were supposed to go on the same day at that time, and we met at Nadia railway station again. I mean, and in the coach we met. At that time, mobile everything were not there, so we didn't have any communication. But then we met at Nadia railway station, and that is how again we ended up into DDIT computer engineering, because I mean that's the native. He was 10 kilometers towards Anand, and I was 10 kilometers towards the other side, but we were localite to Nadia. Okay, but he is right now. I mean, from years. After graduating BTech, I joined DDIT, and then he actually joined System Plus at Ahmedabad, and then he moved on to NVIDIA Pune for years, and then he moved on to USPS development with USA, and then he moved on to Bloomberg, which is a known giant, software giant, technology giant, I would just say. Okay, Bloomberg LP. You might have seen his name on our departmental board, Dhaval Patel. Uh, He's a friend of mine since I would say 99, no 97. Okay, and this is the history I gave you. So he started this Core Basics channel a few years ago, uh, and he's delivering a lot of good stuff, primarily with data science also. He is currently working as data engineer at Bloomberg, and it's been more than I think 10 years. I remember it when I visited him in 2009. He was working in uh, state of Pennsylvania maybe, and then the next year he was state of Maryland, and then he was in state of New Jersey and New York. So this will take benefit of his knowledge. Recently, he was given $2,500 worth GPU by NVIDIA for free uh, for doing some or more AI and machine learning kind of stuff. Okay, so I actually wanted to have with us live during one of our lecture or more, but then because the schedule timetable changed, and I haven't yet got chance to converse with him. But you guys can definitely take benefit of his channel, which is Core Basics. So it's very much I have been personally to his home also, and uh, he's a close friend. Okay. So if you might have any questions, you can definitely post him on the Google YouTube channel. Otherwise, you can pass it on to me, and I can pass it to him also. But then take benefit of that channel. He is really an intelligent guy, I would say. Okay, uh, not many I have seen are near to genius. He is one of them. Okay, so please take benefit of his knowledge in the area of data science. Okay, uh, so we have only a few minutes left, so I will not start talking about a priori, but you have already seen, and this is what the next coming up tomorrow. So for before tomorrow's lecture, which is I think 11 a.m., right? So before tomorrow lecture, I would want you all to learn about what is a priori. Okay, because we are going to talk about something called a priori versions based on MapReduce, right? And this particular was done in October 2018. That means just 2 years down from now. Okay, uh, 2 years ago, and I downloaded this white paper from IEEE Explore yesterday only. So you see this. It was downloaded using our university uh, account. So I can definitely share hopefully, but I still need to read these restrictions, etc. So don't expect me to share this on BDM conduit folder. Don't expect me, because I don't want to get into other stuff, but I can definitely use it for, because it says limited to Dharmestha Desai University, right? So, and you are students of Dharmestha Desai University, so I can definitely take this. I can conduct the lecture. Don't expect me to uh, share this on BDA conduit, please. Okay. So tomorrow in the class 11 a.m. we are going to describe this complete white paper. I said it is not too old. Okay, and what new about it is uh, yeah, these guys are whoever worked on it, but then actually there are few connections also, which is let's just find out. See, it says this cluster which they developed. They did experiment. It was using the operating system ROX cluster, and there is a connection to that in our classroom, Google Classroom. I don't know where will I find that. Have you heard this ROX cluster in the past? Anybody? Okay, so basically, I would have described in the past. I don't know where would I have noted that. I'll have to find that out. But I personally have worked on rocks cluster in the year 2008. Okay, so I mean I was surprised to see that even after 10 years, there are people who have done some research work and know that this research paper we had to download from IEEE Explore, using credentials. It was not freely available. Okay. Uh, Anyways, so tomorrow we'll take this up, a priori algorithms. And there is one more thing. Just hold a minute there. Oh, this process is still hanging. Uh, okay. Actually, what happened 2 years down? I mean, the same around 2018. I believe we had a student named. Okay, I forgot. But then I'm showing you actually. See this particular folder here. I think you are able to see my screen, right? Are you able to see my screen, guys? Right. So see what I just opened. I just opened one of the PNG file, uh, and you see this guy named Sagar. He was with maybe your senior. You may, actually there can be many Sagars, so you may not know exactly the name. But then there was a guy who actually tried developing uh, a priori algorithm with MapReduce locally at our DDU itself. And see, it's 2018 Jan. See, I was surprised, right? He was interested in doing some, work, like research work, 7 semester students only, and he would have given me all these files, so the credit actually goes to him. But I was kind of, guiding him and achieving whatever he wanted to. Okay, so yeah, Sagar Daswani, right? You see this, and that was January 2018, and he would have worked a few more things, but then he tried this Hadoop commands and a priori program in Python. Uh, and we actually realized few we learned few lessons also. At that time, believe me, I never searched for such file from IEEE or anywhere else. So sometimes you have to take the work forward. If you may leave or keep it a break, then you may not achieve what you may want to. Anyways, I'll leave it to the next faculty. Students, tomorrow we'll talk about this research paper. Please go through the channel which I just mentioned, Core Basics, and see if something can help you learn. Okay, thank you very much.
Good afternoon, all. Today's lab is based on the SVM. In last session, the lecture session, Vijay sir has already covered the SVM, right? So, in today's lab, we'll try to explore that SVM. From the shared folder, download the IP file which is given to you. Hope you all are ready and you downloaded the file. So it's 11th lab. Discuss the which is one of the classifier. We're supposed to classify the given data. Previously, we have concluded the discussion of neural network, and later we have concluded discussion of the CNN also, right? That is one model of the deep learning. And we haven't discussed anything related to the RNN. It is generally used whenever you are having a data in sequence, maybe a text or a video or maybe a time series data. And so in such scenario, probably you cannot use CNN with very good accuracy or with very good efficiency. So in that case, people are moving to the RNN. So we do not have time to discuss RNN more. Many of the might be in lecture 2. In Bridges section, after this, there is started any other topic or what was the content of last lecture? related to PCA? Let me know once you get the proper clarity in audio. Okay, so eigenvectors as well as dimensionality reduction. Fine. So probably in the next laboratory we'll discuss about that PCA, right, which is based on this eigenvector and is actually used for this dimensionality reduction purpose. And now today for this SVM, probably your work is more than mine. That is, the file is already given to you, and since so many labs, you know how to create the model and how to train that model. So today for this SVM, what I expect is first I'm giving you some time. You need to explore the maybe you can try it on the internet too and try to fill the blanks, right? So since the since last 4 to 5 lab we are doing the same exercise. We have some blanks in the code and we are supposed to fill that blanks, right? But the comments are given to you so that you can able to identify what should be the probable step that you need to perform. And so for this lab, that's the aim that you need to do. And probably for the next lab, I'm thinking about the PCA, right? As PCA is a part of your syllabus, so anyhow we have to cover that in the laboratory. But we'll see if we can complete that PCA a bit faster. Then we might have some overview of the RNN, maybe one small exercise or one small example situation where you can use that RNN model. Right? We cannot definitely cover the LSTM and GRU model, but at least the basic RNN model and why there is a need to introduce LSTM in the GRU. At least if we can reach up to that level, then also it's good, right? But we'll see how much we can cover in the next laboratory. But for this lab, we'll stick to the SVM and next PCA plus if time permits, then probably the RNN model. Is it fine, Kata? So now this laboratory, it is in two part. In the first part, the one file which is given to you, that is 1-svm.ipynb. Over there you need to complete the code and you need to design your SVM classifier. You can use any of the kernel, maybe the linear polynomial or the RBF kernel. Right, so try to complete the code in the first file, and maybe after half an hour we'll discuss that file, and next we will see on manual data, or let's say on some specific data, how we can apply once again how we can apply the SVM, and how can you choose the kernel, that is in which situation this linear would be appropriate, in which situation the RBF is appropriate, and so on. And so initially this key terms related to the SVM is given, that is what is hyperplane, the support vector. You might aware about all this terminology, right, as it is discussed in the lecture. I guess there is no need to revise any of this concept, right? What is margin, what do we mean by kernel, and the equation as well as the definition of these three kernels are given: linear, polynomial, and the RBF kernel. Fine. So just go through that, spend some time over there, and then look at the code which you need to complete. And maybe you can just try the basic version, that is a linear classifier, right? Just create the linear classifier, fit your training data, and apply the prediction on the test data. And then the rest of the code is already given to you. That is, the plotting related code is already given to you. And in this file, two parts are there. In the first part, manually created data where we have the blob and purely, or you can say properly separated data are there. So definitely you can use a linear classifier, right? And in the second half, or you can see in the second part, we are using the data set from the sklearn library, and once again using that train test split, you are supposed to split the data. And lateral, using, once again you can try the linear kernel over here, and you can see the performance. And lateral, you can try, you can observe the performance difference of the linear and the other two classifiers, sorry, other two kernels. And post your doubt in comment, if any.